So this is an area that has clearly had impact, but I'll give you a history of it also a little bit. But before that, let's wrap up prefetching, as I said. And for prefetching, we've covered a lot. And these are some slides that I added this year. We normally don't talk about instruction prefetching, but I think it's good to talk about it a little bit also because it's an important area. Maybe it has less potential, in my opinion, than data prefetching because data is very wide, right? Data sets are huge. Instruction sets are usually smaller, but that doesn't mean that all instruction sets are smaller, especially with, let's say, code bloat and these languages that make programmers' life easier. There's a lot more instructions to process. And also, I guess in some models, some execution models where you execute short pieces of code and not very long pieces of code, instruction prefetching can be very, very beneficial. But essentially, instruction prefetching, the key idea is very simple. You predict which instructions will be needed by the program and fetch them proactively, as opposed to data. And all of the questions we discussed apply. All of the techniques we discussed apply. The major difference from data prefetching is instructions are really accessed sequentially, whereas data, not always the case. In fact, not usually the case. And this happens because of the von Neumann model, right? There are two key principles of the von Neumann model. If you took DDCA, you would remember those principles. Anybody remembers those principles? Anybody take DDCA? One is a sequential execution, and the other is a stored program computer. You store the program and you execute it sequentially, essentially. Unless, of course, there's a control flow change. When there's a control flow change, there's an explicit redirection of the program counter. In fact, program counter, the program counter points to the current instruction that's executing, right? It's called a counter because you sequentially increment it, essentially, normally. And that's why instruction prefetching sequentially works very well. But of course, when there's a control flow change, this is broken. So you need to predict the branches and figure out where the next instruction may be coming from. Because of the sequentiality of the sequential nature of instruction execution, simple streaming or next line prefetching is usually effective. But we will see a little bit more than that. So next sequential instruction prefetcher, we've seen next sequential data, essentially always prefetch next n instructions, in this case, after a demanded instruction. This works well when program executes sequentially without branching. Right? We've seen this for data also. If you're streaming through data, this also works nicely. And this is actually a very old idea. The first incarnation that I know of is really IBM 369091, which is a beautiful processor. It's one of the first out-of-order execution processors. It's not the first, but it's one of the first. And there's a beautiful paper that talks about this. If you're interested, you can read one of these papers. It also implements Thomas Sowell's algorithm. But you can see that there's instruction fetch buffers over here. But those are really, some of those are really used for prefetching. And again, I will not go through this, but at the time, processors used to be less complex, where you could actually specify the flowchart of the sequential instruction supply function like this. And you can read it if you're interested. They actually look at whether the bus bandwidth is available to the next level, and then they decide to do the prefetching, etc. But today, it's very difficult to specify things like as easily like this. It's good to think about that. This is from 1967. Okay, so people have been doing actually sequential instruction prefetching for a while. These are more recent papers. Again, I will not go through the details a lot, but a lot of ideas that we've discussed apply. So, okay, you don't want to prefetch every n blocks when you're prefetching next sequentially n blocks. Maybe you want to figure out which ones are actually going to be useful. And one way of figuring out which ones are going to be useful is whether the instructions that you have prefetched last time were used before. So basically, you add some metadata into the cache or the prefetch buffer, and you basically keep track of which cache blocks that you prefetched were useful using one prefetch bit for cache line. And if you think, whenever you go through those instructions again, you decide which ones to prefetch and which ones not to prefetch based on past useful. So somewhat similar to throttling that we have used, but it's a little bit different also in nature. So this aims to be more accurate than a naive prefetcher, next n-line prefetcher. I don't know why they did just 4 lines. It's a little bit hard-coded. I don't like that kind of hard coding in general in papers, but that's how it is. But of course, the downside is now it's more complicated. You need metadata to identify which blocks are used, right? But that was true for feedback-directed prefetching, right? As we have discussed, right? That worked. And then people also applied other ideas like correlation prefetching to instruction prefetching. This is an interesting paper that talks about, again, building on the next n-line prefetcher. They basically say next n-line prefetcher might be late because, again, you're running ahead, and as a result, by the time the prefetcher starts the next n-line fetches, the instruction engine is already there, almost, right? You don't essentially, you're not timely enough. So in this paper, what they do is they essentially do correlation prefetching. They identify an iCache misaddress. Basically, they correlate. Whenever they find an iCache misaddress, they correlate it to an early enough iCache access that hopefully is going to cover the latency of the prefetch. That's the idea. And for that, they have some mechanism to predict or calculate how long an iCache miss will take, etc. You can take a look at it if you're interested. But the basic idea is correlating a cache miss with a much earlier access so that whenever you see that access again, you start that cache miss next time. So it's very similar to Markov prefetching in a sense, right? We've discussed this idea, except it's specialized and applied for instruction prefetching. And you can read the paper. I'm going through these quickly. You could actually imagine other ideas. But I'm going to talk about one thing that is actually employed, that has been employed in many processors, which is fetch-directed instruction prefetching. At the instruction level, whenever you're in the front end of the machine, you have actually a lot of information about what you can do. And fetch-directed instruction prefetching essentially executes or exploits that information. So the key observation is that whenever you execute instructions, you essentially have a series of consecutive cache block accesses you have because it's all sequential cache blocks. But then there's a gap sometimes, meaning you jump somewhere else in the program due to control flow. If you can somehow identify those gaps and predict those gaps, you can actually prefetch things early. So we already do that actually with branch prediction, right? Branch prediction already does that. So the idea over here is to run the engine, run the front end of the machine faster, and prefetch the instruction to a queue. While the back end of the machine is stalled, you can keep prefetching instructions to this queue, and you can keep predicting. So the idea is actually really decoupling the front end of the machine and the back end of the machine. Back end of the machine can be stalled for many reasons, as we have discussed, memory, for example. But front end of the machine can keep going almost forever. The back end of the machine can be actually stalled for 1 million cycles, but the front end of the machine can be fetching instructions, predicting branches, and execute, essentially going through the control flow of the program and feeding instructions into a queue, which is the fetch target queue, for example, instruction buffer, as long as it can actually predict instructions and keep fetching. This way, what you can do is while the back end of the machine is stalled, you're really overlapping the latency of the back end execution with the latency of the instruction cache misses, right, if you're thinking about it. And this way, you can also overlap the latency of the branch predictions. So this is a general idea of decoupled front end. You're really decoupling the front end from the back end with a queue in between. And and by doing so, if you're really bottlenecked by the back end, hopefully you'll not be bottlenecked by the front end, unless you mispredict branches, of course. Whenever you mispredict a branch, these things may not be very useful, right? Okay, so I've already described actually a lot of things that are going to come in the next slides. But if you look at the execution of a program, these are basic blocks, control flow blocks. You can see that there are a bunch of instructions, and there's a branch. There are a bunch of other instructions, there's a branch, and there are a bunch of instructions, there's a branch. So what you're really trying to do is go through this basic blocks. And the instruction stream may look like this. You basically predict this branch taken and this branch also taken. And the idea, as I've kind of said, is you direct the prefetcher by predicting branches among prefetched instructions. This also could be called branch predictor directed instruction prefetching. But as I said, it's a more common philosophy, not just directed at prefetching. The philosophy is really decoupling the back end of the machine from the front end of the machine. That's really the principle. And that actually provides a lot of other benefits, like running the front end faster while the back end is stalled, or running the front end while the back end is stalled. And that way you can actually prefetch instructions and predict branches. Does that make sense? Okay, so it's a very simple idea if you think about it, but I'll show you some interesting results from a recent paper from ARM, which shows that this idea if you actually implement it nicely, maybe you don't need other prefetchers for instructions. That's what they suggest. If Rahul was here, we would also ask his opinion. He's not here. Okay, so basically, I think I've already said this. From the current instruction, you start prefetching sequentially. If you encounter a branch instruction, predict the target address of the branch and keep prefetching sequentially until you encounter another instruction. This way, fetch engine can run far ahead of where in the program the execution units are currently executing. And as I said, this is decoupling the fetch engine from the rest of the pipeline. And what do you do with the instructions that you prefetch? In this case, you put them into a fetch target queue. And this target queue is really a FIFO queue. It's really the predicted instruction stream. And you can also decode them, actually. You could actually put the decode stage into the fetch part as well, as long as you need to decide where the decoupling happens between the back end and the front end, of course. And the next stage, it could be a decode stage, or it could be the rename stage, for example, in an out-of-order execution processor, consumes entries from the fetch target queue and processes them. There should be processes them over there. Okay, so this is an example. Probably a picture is worth 1,000 words over here. Here, there's a fetch target queue. This is one example implementation. It's not the only example. I think there may be better implementations, actually. This is from a recent paper that talks about it. Essentially, you have a fetch target queue. It creates a bridge between the instruction address generation unit and the instruction fetch unit. And what you do is this address generation unit keeps on generating instruction addresses using the branch predictor. And essentially puts the instruction addresses over here. And then the prefetch requests are sent to the iCache, and the instructions are essentially buffered over here or over here. Okay, I'll go through this relatively quickly because I've described the ideas essentially. So once you have a misprediction, of course, there's a downside, right? This decoupling doesn't help if your branch predictor is not accurate. If you have a misprediction, you're back to square one. Your fetch target queue is flushed after every instruction that comes after that mispredicted branch is flushed, and you'll need to really start fetching instructions again. So mispredictions are not useful for this case because you're really using the branch predictor. Okay. So this is an old idea. This is one of the papers that described the idea. As you can see, it's from 1999, and it talks. It received a Test of Time award, deservedly recently. You can read that paper, and this is implemented in many processors today, especially IBM processors were one of the first to implement this. These are not the oldest papers, but you can see that they've been implementing in the Z series, their mainframe processors for a long time. And they actually have a very sophisticated front end that they used to describe in some old papers. It's not just IBM, it's also AMD, ARM, Samsung. They've publicly shown that they've implemented this fetch-directed instruction prefetching. Now, the interesting thing is, if you have fetch-directed instruction prefetching, how do you combine it with other prefetchers? So this paper from ARM recently showed that if you actually implement fetch-directed prefetching with a large fetch target queue size and with good enough branch prediction accuracy, maybe other instruction prefetchers are not that good. So this is data from their paper. We have not verified it. Essentially, if you have a small fetch target queue size, and if you disable fetch-directed prefetching, you basically have very big differences between different prefetchers. If you have a very large fetch target queue size, buffering of instructions between the decoupled front end and back end, and if you enable fetch-directed prefetching, essentially there is not that much difference between different types of prefetchers. These are different types of prefetchers. You don't need to know exactly what they are. So this is interesting, I think. It's good to think about how do you design the front end, right? So jury is still out over here. Any questions? Yes. Yeah. Yeah. Mm-hmm. Yeah. Yeah. I mean, basically, the same, everything we discussed about memory applies to instructions also, right? If you miss in the instruction cache, then you have to go to memory. It takes a long time. The question is, how often does that happen? I think that's what you're asking. And the answer is, it really depends. if your workload, for example, has a small instruction working set, very high locality, which is usually the case actually in general, then this is not a huge problem. But there are some workloads where the instruction working sets are actually quite large. Some commercial workloads, for example, some database workloads where you actually keep doing a lot of different things in the workload, then you're touching a lot of different places in the code. This may not fit in your iCache. And also it may actually cause a lot of, let's say, accessing different parts of the code. In that case, this is actually a problem. And these papers talk about that problem. And it could be as bad as the data problem, actually. One of the downsides of instructions that's different from data is essentially with data, you can overlap that latency more easily. With instructions, if you have an instruction cache miss, you're not filling the pipeline anymore, right? So it could be more severe. But the occurrence, I think the frequency of occurrence of instruction cache misses are, in general, much lower than data cache misses. That's why we deferred it to this late. And we have not talked about instruction prefetching as much in prior, let's say, years. But I think it's important to talk about it. Okay, any other questions? That was a good question. People are still trying to wake up from the hibernation in the cold. Okay, it's going to get colder. Okay, so there's more recommended material on prefetching. Some things we have not covered are in old lectures, but I'm not going to talk about that. There are a lot of interesting things here, but we don't have time. If there are no questions, I'll very quickly pitch. If you want to do research in these areas or other areas, talk with us. I know some of you are talking with us. Basically, we do research in all aspects of computer architecture, not just memory-centric aspects, processor-centric aspects also. In fact, we're going to talk about some papers, so think about that. And also, I think one of the things that's interesting with prefetching is I cannot really classify prefetching as a completely processor-centric aspect given a memory-centric computing system, right? If you have processing near memory, processing in memory, you may still need to do prefetching, right? Prefetching by itself is not processor-centric because you may need to execute something in memory, but then the data may not be there, right? Basically, it's really targeting the data may not be there problem. And data may not be there for many different reasons, not because you're processor-centric. It's because someone else modified the data, as we will see later on, for example. Right? So I think this is an area that needs to be re-examined a lot in more memory-centric computing systems. And I think that's true, actually, for a lot of the processor-centric concepts. Okay, prefetching may be somewhat processor-centric comparatively, but there are a lot of other processor-centric concepts, like caching, for example, like out-of-order execution. They need to be re-examined within the context of memory-centric systems. Okay, so we're always looking for bright and self-motivated students who have a passion for rigorously solving problems, hopefully, and who are willing to do proper justice to scientific exploration, evaluation, and communication. And as opposed to what you may hear, unfortunately, we cherish working with everyone all over the world. There's no, basically we can get students from all over the world and we work with them. There's no discrimination with diverse backgrounds. And I think we have an open and inclusive environment that fosters and values creativity, free exploration, collaboration, and rigor. So if you're interested in all of this, work with us. And we've already covered some of these slides, so I'm not going to talk about this, but you can read more about us in the newsletters. We have actually quite a few of these newsletters right now, starting from 2020. And we have some new alumni. Recently, we've graduated 2 PhD students and a postdoc. They go to different places. Again, I'm not going to go over them, but I'm proud of all of them. And you can learn more about us from clearly many lectures. And this is a recent interview and a bunch of other interviews, etc. Okay, so basically, if you're interested, email me. Take our courses online or in person. I think critically reviewing papers and trying to develop ideas is a really important component. So if we interview, for example, we'd like to see how you're thinking. You may not have a lot of background, but how you're thinking is really important for me, for example. That's kind of thinking is really important. Okay, again, I'm not going to go over this because we've talked a lot about this and we have a lot more to cover, but you can find this information. The one thing I will mention, we have some thesis page online. This is not very up to date. We actually do a lot of work, but it's very difficult for us to keep a thesis page separately up to date. So if you're interested in these general areas, you should just talk with us, right? And then there's also this opportunistic nature of research. I think a good researcher is always opportunistic, meaning they don't say, oh, I work in these areas only. There's maybe some other area over here, right? That's actually very interesting. And that area may be brought in by clearly exploration. But that could be brought in by new people who may have new ideas or interest in different areas can enable exploration. It's essentially a machine learning system if you think about it, right? You're working in one area, you develop expertise, you keep exploiting that expertise and clearly exploring within that expertise. But then there's some other exploration happens by randomly or somewhat randomly or guidedly choosing some other areas, right? So it's good to think about that. So that's one of the reasons these thesis topics are not up to date. And the other reason is we're busy doing research. We cannot update all of the thesis over there. And some of the thesis just happen naturally. In fact, I think the best research really happens organically. You come and you have some idea, maybe, or you have some topic that you want to work on and you study it, you study a bunch of papers and you say, oh, I have a better way of solving this problem. What is this fetch there instruction prefetching? I can actually do this much more efficiently, right? And that's the kind of research that can have a lot of impact in the end, I think. But that's not the only way of doing it. Okay, so we have an application site, especially for people who are online. But if you're here already, then we can talk to you. Any questions on that? Otherwise, I'm going to jump into parallelism, heterogeneity, and bottleneck acceleration, which is a different topic, but it's a very core topic, I think. We're going to talk more about parallelism after today also, after we finish bottleneck acceleration. But I wanted to do this bottleneck acceleration first because it's going to make all of the other topics go a little bit faster, in a sense. We're going to accelerate some of the bottlenecks earlier, and then we're going to talk about other topics that are related to this a little bit more. I mean, clearly we've been talking about parallelism, but we're going to talk about a specific type of parallelism today, and we're going to try to analyze parallelism. And we're going to be more processor-centric, but the heterogeneity concept itself is not really processor-centric. So this is our agenda. We're going to talk a little bit about issues in parallelism, and then talk about heterogeneous multi-core systems, their evolution. As I said, I was giving this lecture like 15 years ago, and I was talking about heterogeneity. I was actually giving lectures on asymmetry everywhere. You can find some of the slides in the back. And we were doing a lot of work in that area also. And there were clearly people saying that this is complex. We don't want to design multiple cores, etc. But now everybody's designing multiple cores. And there's a good reason for it. There are multiple reasons. I'm going to give you one of the reasons that I believe is very important. One of the general, not just a single reason, but general collective concept of reasons, as you will see. And then we're going to talk about bottleneck acceleration in more detail. These are some of the readings. As you can see, we're going to cover some of these. But let's start with heterogeneity, even before we start with parallelism, because we're going to talk about parallelism later on also. So heterogeneity essentially is, I use the word heterogeneity, but we use asymmetry interchangeably. In my opinion, they have the same meaning, at least for the purposes that we're going to use. And it enables specialization. So contrast heterogeneity with homogeneity and symmetry. Essentially, homogeneous means everything is the same, right? Symmetric means everything looks alike, right? This is really a system design concept, a very general one, like a lot of the concepts we've been discussing in this course, and also a life concept as well. Essentially, the idea is instead of having multiple instances of a resource to be the same, in other words, homogeneous or symmetric, design some instances to be different, i.e. heterogeneous or asymmetric. This is the design perspective. The other perspective is, because I cannot design all of the resources to be the same, I'm going to let them to be different, or I don't have any control, right? You can also think about it that way, right? And we've kind of seen that, right? With refresh, for example. I cannot make every single DRAM cell the same leakage, so I'm going to live with whatever I have. Now, this is a heterogeneous environment, clearly. There is a lot of heterogeneity in DRAM. What we do is treat it homogeneously, meaning make the refresh equal for everything. What I'm going to talk about is really exploiting that natural heterogeneity. So we have already seen exploiting natural heterogeneity. So essentially, heterogeneity exists in nature. I think of like transistors as nature, but you will see that heterogeneity exists among people also, as you can see, right? The question is, are you exploiting it in a heterogeneous manner? And we have seen that in refresh, retention-aware intelligent DRAM refresh. You refresh the cell according to its leakage. So now that's a method that exploits heterogeneity to gain benefit, which is energy, power, performance, quality of service. But then you can also design things to be heterogeneous. And we have also seen that, right? We've seen, for example, tiered latency DRAM, right? Adaptive latency DRAM. Adaptive latency DRAM actually is exploiting natural heterogeneity, but tiered latency DRAM is really designing a subarray to have two components. One is fast, one component is fast, the other component is slow. Now you added heterogeneity. That's a very conscious design. Right? Okay, so you can design heterogeneity or you can exploit heterogeneity that's already present. Now, regardless of whatever you do, different instances can be optimized to be more efficient in executing different types of workloads or satisfying different requirements and goals. And we've seen this already. We're going to look at a more specific instance. Essentially, the fact that different instances can be optimized for different purposes enables specialization or customization. So why do you want to do this? Essentially, there are two major reasons. We've already kind of seen that also, but I'm putting this into words right now. Different workloads executing in a system can have different behavior. And systems are designed to satisfy different metrics at the same time, right? So the first one, different applications can have different behavior. Different execution phase of a single workload or single application can have different behavior. The same application executing at different times can have different behavior due to input set changes or dynamic events that the application sources, right? There are many examples of this, like locality, predictability of branches, instruction level parallelism, data dependencies. Again, I'm not going to talk about this, but we're going to cover serial fraction and parallel fractions today. Interference characteristics that we may have seen. And also systems, whenever you design a system, you're really trying to satisfy different metrics at the same time. When we design memory controllers, for example, we said we want performance, but we also want fairness. And then we also want low complexity. And you can keep adding more and more, and that kind of leads us to more heterogeneous design, as you have seen. There's almost never a single design goal, depending on the design point. If you remember the earliest lectures, we had a list of metrics, like maybe 10 metrics, but clearly 10 is not enough today. And here, there's more. Okay. So basically, the problem with symmetric designs is it's really trying to fit everything into one type of design. One size fits all. I already said this. To all workloads and metrics, you're trying to fit that design. But it's very difficult to come up with a single design that satisfies all workloads, even for a single metric. So assuming you don't care about any other metric but performance, a single design is still not good enough. And we're going to see that today more. Now, this becomes even more difficult when you actually have multiple design metrics. If you want to really get the best of multiple design metrics at the same time, a single design cannot satisfy this. Another example, we discussed, for example, the machine learning inference accelerators, right? We talked about Google Edge TPU, if you remember. And a single monolithic processor-centric design was not able to really cater for many different types of machine learning models and layers. So we decided to add heterogeneity into the accelerators. So we designed 3 different accelerators in that particular case. One of them processor-centric, 2 of them are data-centric. And the goal was to really satisfy different parts of the workload so that you can get better performance and better efficiency at the same time. And we also gained area efficiency, if you remember. But of course, the cost was always complexity. And you need to decide what to execute where. And that's not going to change here also. The cost is going to be complexity, and you need to figure out what different component to use for a given thing, task, for example. Okay, so this holds true for different system components or resources. Essentially, everything can be re-examined to be heterogeneous, and also policies and algorithms. It's kind of like a general principle, right? We've talked about a lot of general principles in this course. Memory-centric computing was one of them. I think heterogeneity is also an all-encompassing principle. If you look at all resources, they could all be heterogeneous. Of course, this will increase complexity, yes. Okay, so let me give you a pictorial example. Again, a picture is worth probably 1,000 words. This is symmetric. This is a slide that I prepared in 2008 or so. You can see that in this case, it could be cores, but it could be anything actually. It's one size fits all. And energy and performance is suboptimal for different workload behaviors, essentially. If your workload needs greater than this box C, for example, too bad. You don't have anything that is greater than this box C. If your workload doesn't need as much as C, it needs 1/10 of the C, too bad. It's wasting resources of the C, essentially. So if you do asymmetric, this is one example where this could be static, or it could be dynamically configured to be asymmetric. Essentially, this enables now customization and adaptation, right? Because processing requirements vary across workloads. You can find that one workload that needs something as big as C1 should be scheduled here. One workload that needs something as small as C5 is scheduled here. Right? Of course, you can actually go even lower, right? Okay, basically, hopefully you can get minimal energy and adequate performance by doing this. Okay, but now you've also seen that complexity increases, right? What is the granularity at which you do this? Is it static? Is it dynamic? So there are a lot of actually interesting questions that open up. Okay, we've already seen examples before. I'll go through this relatively quickly, but something that we have not seen in this course, this is actually a very old principle. If you've taken DDCA, we've talked about vector processing, which is really the core of today's GPUs. Today's GPUs are essentially vector processors. Even matrix vector multiply engines are essentially systolic vector processors, kind of. But basically, Cray1, which was designed to be a vector processor, I guess I have it in the next slide, had actually a scalar pipeline as well, because they figured out this wide vectors are not good for scalar instructions. If you're operating on one piece of data elements, you don't want to fetch 64 of them. Or you don't want to waste 64 functional units for executing an instruction that requires a scalar value. I'm going to show a picture of this you may have seen earlier. So modern processors also have scalar instructions and SIMD extensions, which is essentially very similar to Cray1 design from 1970s. We've seen decoupled access execute in DDCA again. I don't want to go through everything over here, but basically you specialize the access part of the pipeline to memory access, and then you specialize the execute part of the pipeline to execution instructions. All of these ideas are employed in existing processors to different degrees. We've seen thread cluster memory scheduling, so I'm not going to talk about that. RAIDer, heterogeneous latency DRAM, hybrid memory systems, and there are many different types of hybrid memory systems that we have seen also. Heterogeneous cache replacement policies, this is not up to date, as you can see. We've seen hybrid prefetching earlier also. All of those are heterogeneous examples. And these are all employed actually in real systems. And people don't think about complexity as much, right, when they actually do this. Well, they do think about complexity, of course, but they actually make the decision to actually have heterogeneous components. Okay, so this is the Cray1 picture that you had seen in DDCA, which I find fascinating because this was designed to be, this is the supercomputer of the day, right, 1970s. And you can see that this is the vector processor, which is the major chunk. It has 8 64-element vector registers. You operate on 64 elements at a time. But if you're operating on one element at a time, you don't want to use this because it's very wasteful. So they added scalar registers. And this is heterogeneity at the ISA level as well as microarchitecture level. It's not only that they added those scalar registers, they made that scalar part of the pipeline the fastest of its time because of what we're going to talk about later on today, which is the serial bottleneck. Seymour Cray was a very smart architect. He was more of the, let's say, intuition-based architects who has been designing things. So in my opinion, he's kind of like an architect that can make decisions without requiring a lot of data. This is also good to think about because you cannot predict all the data in the world, right? You're designing a computer for 20 years down the road, maybe. Can you really have data to actually make a decision? That's also true for architects who design buildings, for example, right? They design buildings based on some intuition. Also, of course, there's math, et cetera, involved, but they cannot model everything. It's impossible. Hopefully, they model earthquakes. That's not true in all parts of the world, though. Sometimes they claim they model earthquakes, but then, you know. Okay, so basically going back, they designed this vector processor. The goal was to execute scientific code fast, which is parallelizable code. But they figured out quickly that the real bottleneck, assuming once you accelerate the vector code, is really the serial part. So the serial part, sequential bottleneck, we'll see that also. We'll accelerate in a different way, but we'll also use the same principle of heterogeneity here. They basically said, oh, we really need to execute scalar code also fast. That's why they designed the scalar pipeline to be the fastest of its time in the 1970s. So it was the fastest vector processor and also fastest scalar processor of its time. Okay, so we've seen hybrid memory systems. We've seen thread cluster memory scheduling. Basically, our goal was to design a policy that's good for different metrics and different threads, if you remember. And we've used heterogeneous policies for that. Again, I'm not going to go through this in detail, but clearly there's a lot of heterogeneity in this policy. Well, there are different policies for each cluster, in fact, right, if you remember. And then we've talked about radar. We've talked about tiered latency DRAM. These are just to jog your memory. These are all heterogeneous designs, essentially. Okay. There's something that we're going to cover in later lectures, which is actually very important. Interconnects. I've been trying to push interconnects earlier in these computer architecture lectures, but sometime we need to figure out how to do that. Interconnects are actually very important because this is part of the communication bottleneck. And there are heterogeneous designs for this also. I'm not going to go over this right now, but depending on the access patterns, communication patterns you have, you may want to have different types of interconnects. For example, this Tylera design from 2000s, early 2000s. If you're streaming data, the communication pattern between one core and another core is streaming. It's much better to have an interconnect that's kind of dedicated to that streaming data. And we'll see that circuit switching is one way of satisfying that. For other data, maybe you need different types of interconnects. Basically, they had 5 different types of interconnects, networks on this chip to deal with 5 different types of packets, cache requests versus responses versus IO versus core-to-core messaging versus streaming, essentially. Okay. There's also examples from real life that we could do a lot of, but I will go through this again quickly. It's abundant in real life. We're all heterogeneous. Genomic variation, for example, right? Also other variations. Cells are heterogeneous. I like this example also. These are specialized for different tasks. You have a lot of different cells. Organs are heterogeneous. Cars are heterogeneous. You can imagine why, right? The buildings are heterogeneous for different purposes. Rooms are heterogeneous, etc. Okay, I don't want to harp on this more. Okay, now let's go into a little bit more. Essentially, asymmetry is really a way of enabling specialization, right? There's always this tension between general purpose and special purpose. It's always been there. Since computers were being, let's say, implemented, initial computers were actually quite special purpose, right? They used to do signal processing for some tasks. They used to be analog, etc. And over time, people said, okay, we don't want to design a computer for every single task. So general purpose computers started to dominate. But now we're actually back in a, if you look at the historical perspective, we're in a position where probably special purpose is becoming even more important than general purpose. It's already become more important, maybe because of the applications and because of the lack of technology scaling in the general purpose domain. Right? So general purpose has scaled really well because of technology scaling. But then both applications and technology scaling has been pushing general purpose, squeezing it. Now we're actually more special purpose today. So asymmetry is really a way of enabling specialization. It really tries to bridge the gap between purely general purpose and purely special purpose. Purely general purpose, we've already discussed, is a single design for every workload or metric. Purely special purpose, single design per workload, maybe per workload per metric, right? So you could actually have different designs for each workload for different metrics. Okay, so asymmetric essentially kind of is somewhere in the middle. Multiple sub-designs optimized for sets of workloads or metrics and glued together. This is one way of looking at it. And the goal of good asymmetric design, what's happening, is to get the best of both general purpose and special purpose, in my opinion. So let's take a look at the general, overall advantages and disadvantages. So overall, you can enable optimization of multiple metrics, as we've discussed. You can enable better adaptation to workload behavior. You can provide special purpose benefits with general purpose usability and flexibility. That's actually interesting because you have some sets of components and they kind of look general purpose, but the compiler, for example, or some system can actually take care of the scheduling. But there are also disadvantages we've discussed, and overhead and complexity in design and verification is unescapable, I think. There's higher overhead in management, scheduling onto asymmetric components. And there's also overhead of switching. If you want to really switch between components, okay, I execute this workload over here, but maybe now it should be executed over here for whatever reason, because it went into a phase that is better fit for this type of core or cache or memory. Now you need to switch, and there's always overhead in switching. There's no free lunch, unfortunately. And these are the 3 major overheads, I think. Complexity, scheduling or management overheads, and also switching overheads. And we will see this over and over and over in any heterogeneous design. Yes?
You mentioned optimizing for the same system, depending on who uses it. Might require different methods.
Yes.
Is there consideration to have this customization? For example, the person that they decide how fair this should be, how performant.
Yeah.
Is that part of the design space?
That could be, right? Certainly, if that input is provided, you can maybe configure the resources to maximize some of the metrics that are important. Right? You still need to have some asymmetric components that you can play with. So then the system or the scheduling or the task management becomes more important. And they have to really be aware of what metrics are required and then do the scheduling. The design can also be that way, but that's a bit difficult, right? If you actually, like you can, one vision is basically everybody has their own computer designed specifically for themselves. This is actually expensive probably. If you have an FPGA, that could actually enable things, but FPGAs have their own overhead reconfigurability. But if you have an asymmetric design, at least you have space for optimization for the metrics. Okay. Okay, another example. This is actually an old example. Today you have general purpose cores, CPUs and GPUs together, right? This shows heterogeneity in execution models and ISAs. In fact, increasingly we have other things also. But I'm going to contrast this with heterogeneity in only microarchitecture. Basically, microarchitectures may be heterogeneous and something upstream, the compiler or the system can basically take advantage of these different microarchitectures. Here, the programmer needs to write code potentially differently, right? For CPUs, GPUs, maybe FPGAs, etc. Memory-centric computing also adds heterogeneity to the system, right? So if you have processing near memory, we never propose to get rid of everything else, so it's another accelerator potentially, right? I'll go through this also relatively quickly. Well, we still have time, that's good. Essentially, I think we have three major problems in future systems, and they can all be solved with heterogeneity. We've talked a lot about the memory system. We've talked a lot about efficiency, but we're going to talk a lot more about it today. And there's predictability and robustness we've also talked about. Essentially, heterogeneous designs can cater for all of these, more asymmetric designs. But today, we're going to focus especially on efficiency and especially on performance efficiency, but energy will actually follow in many of our results. And efficiency is always an enabler for scalability, meaning if you're more efficient in the execution of your workload, you can finish it faster, and those resources could be available for something else. Or you could use resources in a much more frugal manner. And then if you have a set of budget, you can execute more things in parallel. So scalability is really a function of your efficiency always. And we're going to see really concrete examples from real workloads today. So today, actually, we have a lot of examples of asymmetric designs. This was not the case in, let's say, 2008 or so. But again, I'll go through this relatively quick. These are some early examples of heterogeneous multi-core. But today, I think everybody's doing heterogeneous multi-core, even in like large general purpose systems, as we will see some examples. Okay. I think we've already seen this picture also. There's increasing heterogeneity in everywhere. And that's going to not change, in my view. So this is a real example. I didn't have this example in 2008 or even 2019 or so. But you can see that there's a lot of heterogeneity in this thing, right? There's the high performance cores over here. There's they don't call it low performance cores because that doesn't sound well, I guess, efficiency cores. And then there's the GPU. And then there's other stuff like neural engine. So there's a lot of both microarchitectural heterogeneity, which is between high performance and low performance cores, or large versus small cores, as we call them. And also architectural, like ISA visible, programmer visible heterogeneity, which is GPUs versus neural engines. And that's true for other general purpose SoCs also. If you look at this, there are large cores over here. I can see that they're large. And then there's small cores over here, more efficient cores. And then there are other engines like media engines. There should be some other accelerators over here that I cannot see right now. Okay. Any questions? Yes.
So dynamically configuring
Mm-hmm. Yeah. Mm-hmm. Yeah. Yeah, that's a very good question. I mean, I'm not going to cover some of those things, but that's a very valid question when it comes to heterogeneity, because they could really enable dynamic heterogeneity in a much easier way. I think certainly programming FPGAs or CGRAs are much more difficult in general, right? Whereas if you have a fixed function process, well, I shouldn't call it fixed function, like a fixed ISA. A lot of these FPGAs and CGRAs lack the fixed ISA, and that abstraction level has made programming easier for the masses. I think with FPGA and CGRA, that abstraction level is gone. And that abstraction level, once that abstraction level is gone, you don't have a fixed set of instructions. Now you have to compile your entire data flow program or whatever, high-level program, into the substrate. And we have not, unfortunately, developed good enough flows to enable high performance translation from high-level code to, let's say, circuits. People are working on it. Clearly, there are many people working on it, but I don't think it's there yet, still. Yeah. So that's a good question. I don't know. I think, yeah, I'm not sure if the fabric that is designed today is also the best fabric, right? Because if you look at FPGAs, there's a lot of overhead in really design, right? There's a lot of overhead to execute a simple function. And configuration doesn't get rid of that overhead, right? The area is still large. So I think there are issues in multiple levels. Now, the goal of CGRA's coarse-grained reconfigurable acceleration was to get rid of some of that overhead, right? If you have coarse-grained blocks that have much less overhead depending on what you do, you can get rid of some of that hardware overhead for reconfiguration. But I think the compilation issue still remains over there. And maybe figuring out what are the blocks that should be there for CGRAs has been difficult also, right? But these are all great topics, actually. Very interesting topics. In my opinion, yeah, we need to be more efficient. We need to look at more efficient FPGA designs and also look at how to really compile, but that's also a tough problem. This is an area where abstraction actually helped a lot. The ISA abstraction, it's kind of really nice. You have for a compiler, you have a very nice target. Now, everybody at the higher level can target that thing and optimize that thing. Once that abstraction is gone, what do you optimize for, right? It becomes difficult. You need to know the hardware essentially, right? Which is a very interesting concept, but maybe it's an idea whose time has not come yet. Okay, any other questions? I mean, even this idea took a long time, right? We'll see this asymmetry in the course. Okay, so let me give you some historical perspective. These are actually slides from older times. But essentially, while I was doing my PhD, people were actually working on multi-cores also, and multi-cores were becoming a thing, let's say, in industry, because scaling a single thread performance was not easy. And people were building multi-cores, and these are simpler and lower power than a single large core, and it enabled large-scale parallelism on a chip. And today, everything is a multi-core, of course. But the approach people were taking at the time were actually a more symmetric approach, except for this one over here, which is an interesting exception, which we may talk about when we get to coherence also. So with many cores on a chip, what you want is really scalable performance, ideal scalability. We're going to talk more about that in multiprocessor lecture. Essentially, you want n times the performance with n times the cores when you parallelize an application on n cores. That sounds beautiful. Ideally, that's what you want. This is called linear scaling also, as we will see more. But what you normally get is Amdahl's law. Hopefully people know about Amdahl's law. I'm going to show that. This is really the serial bottleneck. Your parallelization is limited by how much you can parallelize. If there's a part of your code that you cannot parallelize, that really bottlenecks your performance. So you want n times the performance, but 50% of your code you cannot parallelize. Your n can be infinity, and you get 2x performance. And then this is, you can do the calculation over here. 50% of your code is parallelized, meaning 50% you can parallelize an infinite number of cores, that goes to 0. Your 50% remains. So you basically have 100 divided by 52x, right? That's the idea. It's always good to think about infinite parallelization. Now, the problem is not just Amdahl's law. Amdahl's law is very optimistic. I mean, it's a nice way of thinking about, it's a model, right? It's a model of thinking. And not all models are not always accurate, but they can be very useful. Amdahl used his model to argue that, okay, we should really be focusing on single processors. In his 1967 paper, he said, 1965 paper, he basically said, in fact, the title of the paper, it was the validity of the single processing approach. I forgot everything, but I forgot the exact thing. But the validity of single processor approach to achieve large performance capabilities on a chip. He basically said, on many workloads, you cannot parallelize more than 70%. So we should really be focusing on that, getting that single processor right. If you read that paper, you will see. But okay, assuming you got the single processor right, you parallelize your program 100%. You got rid of the serial bottleneck. Good luck. I've never seen anyone to get rid of that serial bottleneck yet, even though they claim to have done so. There were actually, when GPUs were coming out, what some people were saying, oh, this is great, so we're going to get rid of all the bottlenecks. Well, serial bottlenecks are still there in GPUs. But then there are other things, like, okay, assuming you've gotten rid of perfectly the serial bottleneck, there are parallel bottlenecks. There are bottlenecks in the parallel portion, which we're going to focus a lot on today. And we're going to see some of that. Okay, so this is Amdahl's law. Essentially, this says your speed up is limited by the parallelizable fraction of the program. We're going to see this more, but before we see this more, essentially you have a parallelizable fraction of a program. N is the number of processors. The speed up you get with n processors looks like this. You can make sense of this. I already kind of calculated with particular values. F was 0.5 and n was infinity earlier. But basically, the parallel portion, you can parallelize, the execution time of the parallel portion can be divided by n. Execution time of the serial portion cannot be divided by anything, as you can see. That's a model. Okay? So this says that basically, as you parallelize your program, parallel portion goes to 0 as n goes to infinity. Right? And your bottleneck becomes f, essentially. Right? So if you take the limit of this as n goes to infinity, you'll get f. Or 1 divided by 1 minus f. Right? That's what you would get. Okay. So basically, it says maximum speed up is limited by serial portion. In the next lecture, I'm going to show you some beautiful graphs. But you can, again, put some numbers over here. F is 99%. That's a pretty high. You would be lucky if you have a program that looks like this. And maximum speed up you get is 100. Imagine you have a 1,000 core processor, you'll get 100 maximum. You're wasting 90% of your cores, if that's the case. Okay. And that's not all. Unfortunately, there are bottlenecks in the parallel portion also. It's not usually perfectly parallel. We'll talk about more of these, but there's synchronization overhead. These cores, these things that you parallelize across different cores, they need to synchronize with each other, right? We talked about locks, etc. We're going to talk a lot more about that today. One of them may need to wait for another. Now you've serialized that code. It cannot be perfectly parallel if that's the case, right? Perfectly parallel means there is no synchronization, there's no communication, and you're perfectly parallelized it, as we will see. There's no contention also between them, right? So there are three major reasons why a parallel portion is not perfectly parallel, and these are very fundamental. Synchronization, you could also call it communication. Load imbalance, meaning imperfect parallelization. You have one core, you parallelize your code. One core takes 10 seconds, the other core takes 1 second. Why? Because, I don't know, there's some data dependency, and one data is harder to access for one core. There could be many reasons, of course. You have not perfectly divided the work. That could be another reason, right? There could be many reasons. The load imbalance happens because of programmer or the microarchitecture and anything across the stack potentially. And we're going to see that also. Actually, we've kind of seen that when we talked about memory scheduling for parallel applications, right? And the third reason is we've covered this a lot, which is resource sharing, right? These things that you parallelize don't execute without interacting with each other. Apart from explicit interaction, they also implicitly interact in the shared resources. Once you have contention, one core can be delayed over another core. You have serialization, essentially. And that contention that we were trying to solve nicely when we designed memory controllers, caches, etc., leads to this this equation to not hold, essentially. So you cannot basically do a simple f divided by n at that point. So this is actually a nice slide that summarizes all of the caveats of parallelism that I know of. If you come up with something else, please let me know. Then we're happy to modify the slide. The slide has been around for 15 years so far. Okay. Okay, so basically, let's talk about these serialized code sections. Essentially, many parallel programs cannot be parallelized completely. We talked about sequential portions, serial part. I'm going to give you examples. There's also critical sections that we talked about earlier, locks, essentially. Only one thread can be updating the shared data, and another thread that needs that shared data needs to wait. There are barriers when you actually parallelize your program, partition the work, and all of the threads do something, and when they need to go to the next stage of parallelization, they need to do something else, right? For example, I think one of my favorite examples here, okay, I'll give it today, not tomorrow. You have a program that you've written, and your goal is to count the number of letters in a book, right? One way of writing this program is actually take the book, let's say it's a 1,000-page book, and you're dividing it across 100 processors. Give each processor 10 pages. This is actually very commonly used in parallel processing. It's called the bulk synchronous paradigm of execution. You give a chunk of work to each processor, and let's say you sequentially distribute the chunks. The first 10 pages go to processor 0, the last 10 pages go to processor 99. Not a terrible way of parallelization, right? And then each processor counts the first 10 pages. And then after all of the processors finish, you try to merge the results. So the first barrier you get is until all of the processors finish their pages, right? Of course, you can optimize this, like you can a subset of processors, etc. But let's assume that it's a first cut at this program. All of the processors need to reach the barrier, so they update their local histograms of the count of every single letter, right? Did I say word? Letter. It should be letter earlier. So you're counting the letters. Now, all of the bottlenecks exist over here. One processor, the first processor, let's say first 10 pages are empty in the book. What does that do? It's done very quickly, right? It reaches the barrier right away. The next processor, unfortunately, gets the most heavy pages. The next processor gets 5 pictures. So it's also easy. So now you've broken the load imbalance immediately in that picture, right? In that task. And this is a difficult task. How do you achieve load imbalance, right? In this task. Think about it. Even the simple problem of counting letters in a book. Okay, and then when you're updating the histograms, like shared histograms, you need to access the critical sections. And then when you're distributing the tasks to different processors, you have a sequential portion. Who distributes the tasks? Do the processors get their task on their own? Yeah, you can try to parallelize it. And then when you're actually trying to solve the load imbalance problem, what might happen is you may actually add more sequential portions. Because if you want to solve the load imbalance, let's say dynamically for some reason, you figured out, okay, my load imbalance was incorrect. It's very hard for the programmer to solve the load imbalance problem in the problem that I described, right? The programmer doesn't know the input. This may be the 1,000-page book. It may have this imbalance. Another book may have a different type of imbalance, right? So basically, if you're trying to solve the load imbalance problem with some dynamic mechanism, you make your program more complicated. You can do task stealing, for example. You basically chunk things in a way such that smaller chunks can be scheduled to different processors. But then you have overhead of managing those chunks right now. So these are all fundamentals of parallel processing, if you think about it. And all of them are limited by all of these serialized code sections. Okay, serialized code sections, if you're serialized, basically your performance reduces, you waste energy, and you limit scalability, as we will see. So let me give you one example very quickly. It's one of the papers that we're going to ask you to read. MySQL is an open source database. It's relatively old right now, but people still use it. You open some database tables and you perform some operations. You don't need to know exactly what these are, but this part of the program is parallel. This part of the program is more, let's say, critical section based. You need to access this open tables cache, which is really shared a lot across a lot of processors. And whenever you really open a database table, you need to mark it as I opened this database table, so nobody else should really change it, right? So you have actually, you're going to write to this table. So there's a critical section that protects it. Again, the paper has some more detail, but this critical section is really limits your performance. As you add more processors, meaning increase your chip area, let's say, your speed up increases until some point, and then after that point, it starts reducing. And one of the major reasons the speed up starts reducing is processor's content for this critical section. This critical section becomes a bottleneck. I will show you that using simple asymmetric designs can actually increase this. This is an unoptimized version. Basically, you can scale up. This is called a scalability curve in parallel processing. Essentially, you're computing the speed up compared to a single processor version of multiprocessor versions. And this is where the performance scales up to. I don't know what that core is, but 16 cores or so, right? 16 core area equivalents. With an asymmetric multiprocessor, you can do much better, basically. Okay, we'll see more examples. Okay, so let's take a look at what fundamentally do we want, right? Fundamentally, in a serialized code section, you want a powerful large core. Yes. Yeah. This example, okay? Symmetric cores, yes. Exactly. You get worse performance because your bottleneck is really the critical section. And what happens is you're really ping-ponging data. We've discussed ping-ponging in an earlier lecture. We're going to see more. But you're really ping-ponging shared data as well as locks across the processors. There's also contention effects that was also taken into account here, but that's not the major reason why the performance goes down. But this is a very common curve. I mean, in asymmetric also at some point, you would go down, but maybe not at 32 for this workload, right? Okay, that's a very good question. So basically, we want, in a serialized code section, you want a powerful large core. The question is, what should that powerful large core look like? In a parallel code section, we want probably many wimpy small cores, right? Depending on the code section. If you parallelize it really nicely, wimpy small cores could be good. And these two clearly conflict with each other, right? If you have a single powerful core, you cannot have many cores. And a small core is much more energy and area efficient than a large core. So this is what we're going to assume. A large core is a large out-of-order execution core with a lot of techniques for instruction level parallelism and memory level parallelism. Small core is very simple in order. I'm going to show you more examples of this. Maybe not even a branch predictor, right? It may have fine-grained multi-thread. And this is kind of a rule of thumb. It's not, of course, correct for every workload, but this is kind of an assumption that we're going to make for some calculations now. Large cores are power inefficient. Essentially, you get 2x performance with a large core for 4x area. Area could be a first order thing for power, let's say, predictor of power. And these are some results from Intel, actually. This is their paper in 2004. They basically talk about large versus small cores in a different context, as we may see later on. But this is what looks like a large core over here. And this is what looks like a small core. You can see the pipeline with pipeline depth. You can see the normalized performance. I think they're quite optimistic over here with a 5 to 8x. Normalized power is much larger, and normalized energy per instruction over here. So basically, large cores are not very efficient, but they do get high performance. I'm not sure about the 5 to 8x. I don't know what code they're running. Okay, but when multi-core systems were being designed, this was one of the earliest multi-cores, actually. IBM put together a very nice multi-core system in 2000, earlier than 2002, actually. It's a symmetric multi-core chip. Basically, they added 2 powerful cores. This was one philosophy. We're going to keep the cores powerful, but we're going to have few powerful cores. And you can see some of the parameters of the score, which we'll not go into in detail. We've already seen the stream-based prefetching that they employed, actually, in IBM Power 4. But this is, for that time, it's a pretty powerful core. Many cores did not even have 8-wide instruction fetch at the time. IBM Power 5 made each core a little bit more powerful, and they added multi-threading, simultaneous multi-threading. So that was the philosophy, essentially. There was another philosophy, which was Sun, as we've also discussed. These guys were bought by Oracle, unfortunately, as you remember. So they were innovating quite a bit, actually, but they stopped innovation. That's very sad. A company buys another innovative company and makes it non-existent. That has happened multiple times also. I think more recently it happened with VMware versus Broadcom. Broadcom bought VMware, and VMware is dead now, kind of. Yeah, meaning the innovation is dead. So it's good to think about also those things. So if your company gets bought, that doesn't mean innovation in the company will continue. That actually happens in a lot of startups also. Some big companies buy startups to maybe kill the innovation because they're not competitors anymore, right? Okay, it's good to think about it. Sometimes maybe not all systems are designed with good principles in mind. Okay, anyway, going back, Sun, these guys were, actually Sun was a very innovative company that a lot of innovations before this also, but they were designing these simple wimpy core processors. If you look at these cores, they actually had 8 processors over here. Each processor was 4-way multi-threaded. And if you look at a single processor, it's very simple. It's 4-way fine-grained multi-threaded, 6-stage, dual issue in order. There's no branch prediction. There's very little data dependency checking because at any given time you have you don't have 2 instructions from the same thread in the pipeline. So there's no need to predict branches. There's no need to do data dependency checking. This is basically fine-grained multi-thread, as you can see. It even had a shared floating point unit among cores, and that turned out to be a bottleneck. So they actually replicated in the next instance of Niagara 2. So this is a very different design philosophy, as you can see, right? It's very simple cores, but many of them. And they claimed this was good for, let's say, their commercial workloads. But over time, they figured out, okay, maybe this was not that a good idea. So let's improve. Let's make cores more and more powerful. And that's why they were going with run-ahead, for example. They added run-ahead to make each core more powerful. And then they were actually adding this simultaneous speculative threading that I mentioned when we talked about run-ahead to make each core even more powerful. So they figured out these small cores were not really that good in the end because of the bottlenecks. Okay, but ideally, we don't want essentially either extreme approach. Like, what do we want? And remember, these are our demands, right? And we've already said everything over here. The question is, can we get the best of both worlds? Let's take a look at best of both worlds a little bit. So we're going to make some assumptions over here. Small core takes an area budget of 1 and has a performance of 1. Large core takes an area budget of 4 and has a performance of 2. This is the tile large approach like IBM and also other folks. As you can see, these are some early multi-core processors. You get high performance on single thread, serial code sections. You get 2 units of performance. But you get low throughput on parallel program portions, 8 units. Why is it 8 units? Because you have 4 cores and you have 2 units of performance, so you have 4 times 2, right? 8 units. Tile small approach, you tile many small cores. In this case, because of the area constraints, this is area 4 by 4 is 16 base core area, and this is 16 small cores now. Some folks also had this idea. Tyler, we discussed that it was actually ultra small cores. Intel had actually a very interesting project at the time, which unfortunately didn't go through. Their goal was to actually have many x86 small cores to compete with GPUs. Unfortunately, their software stack was not optimizable as easily, so they couldn't compete with GPUs, and this project kind of not died, but kind of transformed into something else that is not as influential at this point. But the point is there was a lot of innovation going on also still. So basically, if you look at this, there's high throughput on the parallel part. If you're parallel, you get 16 units, right, that is working for you. But unfortunately, on the serial part, you get a single thread working on a small core, so you get 1 unit of performance. So your parallel part performance is high, but your single core performance is 50%, right? Okay, so basically, we've already said this, right? This is kind of putting everything in the same slide. Tile large has benefits on single thread, but low throughput on parallel portions. Tile small has high throughput on the parallel part, but low performance on the serial part. And one of the reasons why major companies didn't want to go tile small is you get reduced single thread performance compared to your previous processor, right? Single thread processor, because large processors were there already. So the idea is very simple. You can kind of guess it based on the context of the lecture. Have both large and small cores on the same chip. This is performance asymmetry. So that's what brings us to asymmetric multi-core. I'm going to give you some examples, and then we're going to take a break. But in one incarnation, you can provide 1 large core and many small cores. This is one example, right? You carve out 4 small cores and make it a large core. You can do it statically. Static is easier. You can do it dynamically, and people have actually looked at how to do this dynamically. It becomes complex, but it's possible to do. There's a paper called Morph Core in Micro 2012, if you're interested in that. Before that, there was a paper called Core Fusion in ISCA 2007, which are actually very interesting ideas. But statically, it's easier, clearly, right? You can design a large core statically and maybe multi-threaded. Okay, so if you do this, you can extract the serial part using the large core. So you get 2 units in serial code sections, which is the same as tile large. And you actually get 12 plus 2 units in the parallel code sections. 16, almost 14, which is almost 16. And if you actually play tricks in the large core and have multi-threading, you can actually almost get 16. So we didn't play tricks. So we're not gonna assume multi-threading in the large core, but you could actually assume that, and you're gonna get the best of both worlds almost. So basically, if you want to accelerate serial bottlenecks, whenever you have single thread, execute on the large core. And whenever you have many threads, basically schedule them on the small cores, regardless of your parallels. And then when you get back to a single thread, let's say this is the parallel part, this is the serial part, you go back to the large core. Right? That's the idea. Now, if you do this, I've already given you these results actually. Right? So tile large, tile small, and ACMP. ACMP gets essentially the same serial performance as the tile large approach and almost the same parallel performance of tile small. As I said, this could be increased to almost 60 with multi-threading. We're not assuming multi-threading in the large core. If you assume multi-threading, maybe these can be, you could get 4 units of performance over here, right? Okay. And I think multi-threading is the right approach actually, but we want it to be actually harder on the asymmetric side. So if you modify Amdahl's law for an asymmetric multiprocessor, serial portion is executed on the large core, parallel portion is executed on both small cores and large cores. And L is the number of large processors, S is the number of small processors, and X is the speed up of a large processor over a small one. Now this is what you get. Now 1 minus F, it gets divided by X over here. Our baseline is a small core, of course, right? Whereas this gets divided by something more complicated, which is the number of small processors times X times L, which is the number of large processors times the speed up that you get. But if you assume multi-threading, this needs to be modified a little bit more. So now you can actually draw curves with Amdahl's law, which I'm not going to do. Okay. Other parts of the code actually can also benefit from a large core. For example, critical sections that are contended, parallel stages that take longer than others to execute, they could be shipped to the large core, right? If you have a large core. And we're going to see that. And the general idea that we're going to examine in the rest of the lecture after the break is dynamically identify code portions that cause serialization and execute them on a large core. So this is a good place to take a break. We're going to look at like progressively different ideas, starting with a small one, which is accelerating the serial bottlenecks only, and then do it more dynamically through hardware, software, co-design. But when we talk about these, it's always good to think about, we have looked at one way of doing this, which is really software has a lot of information, provide that information to the hardware, which I believe is the right way of doing it. But clearly, this is not easy to adopt, right? Whenever you modify both software and hardware, you may be able to modify nothing in the end. There are other ways of doing it potentially, like purely in hardware, purely in software. People have also looked at after our works, but that's a bit harder, I think. So we're going to see a lot of ideas. So hopefully you'll think maybe more ideas. But now let's take a break. I'll take questions after the break. Let's take a break until 14:45, 16 minutes, and then we'll continue. Oh, from that room or this? Oh, okay, I see. I see that. Okay. More sequential processing here. I see. Is that a big problem? Could be, depending on the situation, right? Depending on the workload you're executing. Yeah. Okay, well, we have heterogeneity in the rooms. Thursdays here, Fridays there. Okay, so now let's jump into some ideas. I'm going to cover a bunch of readings. Let's see how much we can cover. But this is the caveats of parallelism. Remember, we talked about the serial bottleneck. We're going to start with the serial bottleneck. And I've already given you the idea, actually. But we're going to actually execute the parallel bottlenecks as well. And we've already covered this slide. I'm going to start with the first idea, accelerated critical sections. This is a hardware-software co-design to accelerate critical section execution. But let me give you something that will motivate this. This kind of picture is always good to motivate things. Even though you may not have exact numbers, you may reason about things. Right? For example, let's take a look at a code that has 12 iterations, and 33% of instructions are inside a critical section, which is only one thread can be in the critical section. That's all you need to know to look at this. If you execute this code in one processor, P equals 1, the execution looks like this. The critical section is the red part. Now, if you parallelize it in two processors, you can parallelize the parallel parts, but only one thread can remain in the critical section. So based on this is what you would see, right? But you still get pretty good speed up, as you can see, right? Now, if you parallelize a little bit more on three processors, this is what you get. Again, parallel portion can be executed in parallel, but red parts cannot be executed in parallel. Red parts are serialized, as you can see, always. So you get some more speed up, but not as much as going from 2 to 3, actually. Now, if you execute in 4 processors, you get no speed up. And the reason is when you were at 3 processors, when you were at 3 processors, there was no room for parallelizing the parallel part even more by adding one more processor. If you look at this critical section, there's always one thread that's executing the critical section at any point in time, right? And this is an optimistic example, meaning when you go from 3 to 4, your performance doesn't degrade. In many real cases, your performance actually degrades because basically the reason your performance cannot improve is because you cannot parallelize the parallel portions because you're limited, you're bottlenecked by the critical sections, as you can see. So threads basically weight more. Here, this thread, even though it finishes at this point, it cannot enter the critical section because the 4th thread that you added is in the critical section. Same happens over here. So you basically have some waiting time that happens in each thread because you're really bottlenecked by critical sections. And this is if you're lucky, as I said. In most cases, your performance actually degrades. And the reason is now you're communicating more across different threads, right? Whenever you want to enter a critical section, you need to take a lock. Whenever you access the critical section, you access some shared data. And that needs to be communicated across more processors now. And these processors have their own private caches. So there's this ping-ponging effect that we discussed last time, and we're going to discuss more. So even this is an idealized case. So basically, if your performance is limited by critical sections, and if you accelerate critical sections, this is what would happen. With a single processor, let's assume you have some magic mechanism that accelerates critical section by 2x. In a single processor, you get some performance gain, that's good. In 2 processors, you get some performance gain, that's good. In 3 processors, you get some more performance gain. And now the realization is that with 3 processors, you're not always in the critical section at any point in time. Right? So there's room for more parallelization. If you parallelize more, you get more performance improvement, as you can see. And this performance is, at least in this cartoonish picture, better than 3 processors, right? And you're still not bottlenecked, so you could actually parallelize even more. So this is a nice intuitive example that shows that, yeah, I've already shown this part, I already said. Accelerating critical sections actually increases both performance and scalability, right? Scalability, to define it more rigorously, it's really the number of threads at which your performance saturates, becomes maximum. This could be expressed in terms of number of thread, number of amount of area, etc., as we will see. Okay, so hopefully this motivates. Contention for critical sections leads to serial execution of threads in the parallel program portion. Contention for critical sections increases with the number of threads and limits scalability. This was the data from my SQL I showed you over here, right? I'm not going to repeat the same thing, but basically, this is the reason your speed up starts degrading significantly after, I think, 16 areas. It could be 17, don't quote me on it. As you keep adding more threads in MySQL. And we're going to get something like this. And you kind of already know the idea, I think. So basically, the case for asymmetry is execution time of sequential parts, critical sections, which we're going to focus on, and limiter stages must be short. And you can say, it's always good to actually, when we were doing some of this work, some of the comments that we received was, this is programmer's responsibility. Right? Programmers should do this. But it's very difficult for the programmer to do all of this, actually. First of all, programming is difficult. And then getting the programs correct is difficult. Getting a single thread program high performance is difficult. Now you want the programmer to get the parallel thread performance high and also scalable. Keep adding threads and you're going to scale. And there are many reasons of it for it, actually. First of all, it's difficult, right? The second is maybe the programmer doesn't know exactly about how to optimize a program, right? They need to really be domain experts to optimize a program. For example, some companies, like I'm going to pick on Oracle again, some database companies actually hire a lot of programmers, some expert programmers, who try to minimize these critical sections as much as possible. And they've been doing this for many decades, 3-4 decades or so. And they're still doing it. Meaning this is a difficult problem, actually, even when you have domain knowledge and even if you actually improve the domain knowledge, because it's just the nature of communication and the nature of synchronization across threads. On top of this, there's variation in hardware platforms. Okay, you may optimize for this hardware platform, but another hardware platform has different kind of caches, different kind of synchronization instructions to do the locking, etc., different kind of processors, and then your critical sections become different bottlenecks, potentially, right? It's very difficult for programmers to take into account. Limited resources, meaning what should the programmer really be doing? It's a good question. And on top of this, there's a performance debugging trade-off. Yes, you can always get more performance at the expense of more bugs. And synchronization, this sort of synchronization across threads is one place where you're almost guaranteed to get bugs. How many people have done parallel programming here? Okay. How many people never got any bugs with parallel programming? Hopefully, you're not brave enough to raise your hand, but you can be. But it's very difficult, basically. It's not, it's easy to get bugs over here. How many people have written operating system kernels where they had to really, let's say, synchronize across shared resources, across different threads, allocate resources? I'd recommend thinking about that. Not easy, basically. So you can always get performance at the expense of more bugs. Another way of looking at this is if you actually have a mechanism that provides you better parallel performance underneath, the programmer can be more liberal in the sense that they could say, okay, I'm not going to do aggressive things that will cause bugs, but hopefully I'll get better performance. Right? That's the idea over here. So you're debugging, you alleviate some of the performance debugging problems. So basically, that's why having mechanisms that aid the programmer is much better. Essentially, a mechanism to shorten serial bottlenecks without requiring programmer effort. With programmer effort, you can hopefully do better, but we should aim for these mechanisms in general. This is true for processing in memory, right? One of the issues we discussed with processing in memory is the programming effort, right? Ideally, you would like to minimize the programming effort. Okay, so basically the idea in this work is to extract serialized code sections by shipping them to powerful cores in an asymmetric multi-core processor. Okay, let's take a look at what this idea looks like. Hardware and software cooperatively ship critical sections to a large, powerful core in an asymmetric multi-core architecture. And the hope is that the large core can execute the critical sections much faster. And hopefully that reduces serialization due to contended locks. It reduces the performance impact of hard to parallelize sections. And hopefully the programmer doesn't need to heavily optimize the parallel code. You get fewer bugs and improved productivity. So it has higher level benefits also. And all of this is conditional upon the large core, powerful core executing critical sections much better. So now there are actually interesting questions over here. Can you customize the large core to be much better at critical section execution, right? We didn't do that as much, but I think there's opportunity here also. And maybe different types of code should go to different types of cores, right? So I can actually specialize this. We're going to use general purpose cores in this, but you can actually, I think in the ideal incarnation of this, you really want to specialize as much as possible to the critical parts of the code. Maybe non-critical parts of the code can be executed in parallel processors that are wimpy, but critical parts of the code, those are the parts of the code maybe where you really want to actually accelerate things, right? Assuming you can determine them. So this is the idea, essentially. You have a large processor and a bunch of small processors, and you have a critical section request buffer. Large processor, in the extreme version of this idea, is dedicated to executing only critical sections and also serial parts. Basically, it's a server processor. You send to the server processor things that are critical. You can think of it that way. And all of these are clients, if you think about it. And the communication model is kind of like that also, right? So basically, normally you have an enter critical section and a leave critical section, which enter critical section actually gets the lock and leave critical section releases the lock, assuming you're doing locking. But clearly you can do other types of critical sections like semaphores, etc. And then there's some code in the critical section. In this case, you're inserting into a priority heap, which may take some time depending on the shared data, right? So what we're going to do is processor 2 executes this enter CS. We're going to add an instruction called critical section call to the ISA, instruction set architecture. And processor 2 sends this critical call section request to the CSRB. Essentially, it's a message saying that I want my critical section to be executed on you, right? CSRB is a critical section request buffer. And then at some point, processor 1 schedules that over here. It could be a FIFO queue. We're going to change that queue later on. In this particular incarnation, it's a FIFO queue. And processor 1 executes the critical section. And once it's done, it sends the critical section down signal. And processor 2 can continue. Hopefully that makes sense, right? It's a simple execution model. It's very similar to what we've seen in Tesseract, for example, right? It's remote function call. You're doing a remote function call, especially for critical sections. And you need to provide all the mechanisms to enable this, of course, right? So let's take a look at an example of this in the programming model. Compiler can actually translate everything, of course, especially if you're programming nicely with libraries to do locking and unlocking, etc. So this is what's executed in a small core lock. You acquire the lock, you execute the critical section with some input data that could be generated in a shared, in a non-critical section, And then once it's done, you unlock and then print the result. This is one example, right? Now, what small core does in the accelerated critical sections model is, this is one way of doing it. There could be other ways. We're going to communicate between small core and the large core through the stack, shared memory, essentially. It computes A, which is the data that's computed in the non-critical section. It pushes the value, input value of the critical section function call onto the stack so that the large core can obtain it by doing a pop from the stack. And then it basically sends a critical section call request for this particular critical section, lock X, let's say. And the critical section starts from target program counter. This is the program counter at which the large core should start executing when it decides to start executing that critical section. So this gets sent over the interconnect. You send the X lock, which is the critical section ID, in other words, target PC, the stack pointer, and the core ID. And then this waits in the critical section request buffer in the large core for some time, hopefully not too long. But if your critical sections are content, actually, it could be too long, right? If you have a lot of contention for your critical sections, everybody can be sending requests to the large core. But at some point, the large core decides, I'm going to execute this critical section. It takes it out of the FIFO queue, and it starts executing, basically, from target PC. And target PC code is modified. This critical section code is modified such that you acquire the lock, just in case, because you really need to maintain the semantics of acquiring the lock. And then it pops the input. So if there are multiple inputs, you need to send, of course, multiple inputs. You need to push all of them, and you need to pop all of them. And then you execute the critical section, and then push the result on the stack. You release the lock, and then execute a critical section return instruction, which communicates a critical section down response to the small core that initiated this request. And then the small core pops the result of the stack and prints the result. Looks good, right? So if you're really executing, if you're really programming nicely, this could all be done by the compiler. Clearly, you could all do this as the programmer as well, right? Now the question is, can you do this purely in hardware? That's a tough thing to do, I think, but potentially doable. And people have tried, but one of the issues in hardware is you need to have some instructions that are actually directly locking. A lot of hardware today actually doesn't have lock instructions necessarily. They execute a sequence of instructions that do locking. This is some food for thought, basically. How do you identify a critical section, basically, remains a problem still. We may talk about that more in later, essentially later lectures. Okay, so this sounds good though. It's doable, clearly. So one of the issues that you run into if you do this sort of thing, whenever you decide to execute critical sections on a single core or a server, let's say, actually there was some later work that did this purely in software and across different processors, which showed results that look kind of similar to what we did in simulation. One of the issues that you run into is large core can become bottlenecked, right? If you send too many requests to the large core, you can have bottleneck. Now, this may be okay if all of those requests are for the same critical section, for the same lock. Lots of processors are trying to acquire the same lock. They should be serialized because they're going to be serialized anyway, right? In fact, it's better that they're serialized on a large core with large caches because the critical section lock always remains on the large core, right? This is one of the other benefits of executing critical sections in one place. Lock remains on the same place. It doesn't get ping-ponged. Shared data that you're accessing remains on the same place. It doesn't get ping-ponged. So we actually solved the ping-ponging problem. But it comes at the expense of false serialization, meaning independent critical sections can get sent to the server processor. Now the problem is what happens if you have independent critical sections? Essentially, a critical section B can be waiting for critical section A to execute. And these are completely independent. If they were executing on their local small processors, they would be parallelized completely. Now we're serializing them. Very bad. One way of handling this is, actually there are multiple ways of handling. One is doing multi-threading on the large core, right? Meaning you execute critical section call A concurrently with critical section call B by doing multi-threading, and we do that in some later works. That actually alleviates the problem. Now, the downside is you're not using the entire large core to accelerate a single critical section, right? So each of them can be accelerated less, but maybe it's better than false serialization. So in this work, we have another mechanism which keeps track of how often this false serialization happens. So this is the critical section request buffer. It gets input from small cores. It executes the critical section on the large core. And we have some counters, saturating counters to keep track of how many times a particular critical section was falsely serialized, meaning it had to wait for the large core because some other critical section was executing on the large core. So you get a critical section called A, something happens. You basically decrement the counter because this can be executed. You get a critical section called A. Serializing these is fine. In fact, that's exactly what you want. So you get decrement the counter. Now you get a critical section called B. Unfortunately, this gets serialized, assuming this is a FIFO queue again. You increment the counter. Now, once your counter is larger than some threshold, large core says to the small core, don't send these critical sections to me. And the small core stops sending the critical sections. That's one way of eliminating false serialization, right? You can have a combination of multi-threading plus that, of course. Okay, so keep that in mind. So essentially, the pluses is you get hopefully faster critical section execution. I'm saying hopefully because the assumption always is that large core is faster. But always think, if your bottleneck is really memory, maybe large core is not that much faster than the small core. It's good to think about it. It's still probably faster, but maybe not that much faster. If your bottleneck is really computation, large core can go really fast, of course. The other benefit I already said, shared locks stay in one place, so you get better lock locality. That's actually a big benefit, and we demonstrate in the paper. Once you read the paper, you will see that some benefit comes from making the critical section faster. Some other benefit comes from actually keeping the shared locks and also shared data in the large core's caches. You get better lock locality, better shared data locality, less ping pong. Yes. Could you say it again? Why do you even need locks? Okay, that's a very good question. Basically for correctness purposes. The reason, okay, so we acquire the lock over here, essentially. We discussed this in a footnote in the paper, but there could be, actually there are two reasons. One is false serialization. Once you have false serialization, you still need locks to execute. So there could be some lock executing here, another lock executing here for the same critical section, potentially. And the other reason is really correctness purposes. We don't want to eliminate locks because we cannot maybe guarantee that someone else may not be executing the critical section because there's a large view of the system, right? There may be some other code that's written by someone else that may be locking, right? Potentially, yes. Yes, that's right, exactly. But yes, if you're extremely aggressive, you can get rid of the locks also. And that will actually buy you even more performance. Okay, so minuses. In this particular work, we dedicated the large core for critical sections, meaning your parallel throughput reduces. You may decide not to do that, but then you have a problem, right? You want to accelerate critical sections, and you're executing some other things on the large core. meaning those things contend with the critical section execution. Right? So that's the reason why we decided to dedicate critical sections. But we will see that there are other things you can exploit in this large core when we go to the next work. Clearly, there's some transfer overhead, right? You're transferring the critical section. You're doing a remote function call. You need to send the critical section call and critical section down signals. We're going to analyze those trade-offs a little bit. And then there's also some other thing that needs to be transferred, which is the thread private data, meaning data that you input to the critical section that is generated outside the critical section. This is different from shared data. This is not data that's shared. This is really the data that you're inputting to the critical section to do the computation on the shared data. This becomes worse, meaning it needs to be transferred to the large core. And in this particular case, we did it through push and pop instructions, as you can see over here. There could be other ways. You could directly send data into registers, etc., but that complicates the communication paradigm. But essentially, now you're trading off shared data locality with private data locality. If you had executed the critical section in small cores, private data doesn't need to be transferred anywhere, but shared data now ping pongs. Now the question is, which one's worse? And the answer is it depends. So this is actually an interesting analysis I will show you in a little bit. So these are the performance trade-offs. With accelerated critical sections, you have fewer parallel threads because we're dedicating the large core for critical section execution. But on the upside, we're accelerating the critical section, hopefully. Right? So this is the trade-off. What we see in results, unless you're extremely area constrained, accelerating critical sections offsets the loss in throughput. There's another benefit over here, or trend. If you keep increasing the number of cores on chip, the fractional loss in parallel performance decreases, because hopefully you're not going to dedicate a huge fraction of your chip to the large core for mainly design constraints. It's very difficult to design a large core that occupies a huge area of the chip today, as you've seen in all of the pictures of today, right? Today, even large cores are a very small fraction because people don't know how to design extremely large cores that can take advantage of a large fraction of the chip. So basically, increased contention for critical sections also happens as the number of cores increases. So this trade-off actually is good with technology scaling. It's better to dedicate a large core for critical sections, which can accelerate critical sections. Something is happening here. Okay, the second trade-off is you send CS call and CS down signals as opposed to locking and unlocking. We're still locking and unlocking, but we're adding some more overhead. Essentially, okay, I should say that we're still doing locking and unlocking. Basically, you get better lock locality, right? We're adding CS call and CS done. That's additional overhead, but we also get better lock locality. And essentially, we avoid ping-ponging of locks. So there is clearly a trade-off over here. And then let's take a look at the last one. If you get more more cache misses for private data, because we're communicating that, because it's the private data is actually produced in the small core, and it has to be transferred to the large core, right? But we hopefully get fewer misses for shared data, because now, assuming you execute all of the critical sections in the same core, the shared data always remains there, right? It never needs to be communicated somewhere else. Okay, so let's take a look at cache misses for private data. Usually, the cache misses for private data is actually a smaller fraction, but not in all cases. It depends on how much the programmer optimized the code, etc. In some cases, the programmer has a large critical section, and lots of things are private data inside the critical section, etc. Okay, so let's take a look at one example over here. If you're trying to add, for example, a node to a heap, the shared data is the priority heap. Private data is hopefully one element. Assuming your shared heap is large, when you add this private data, you actually touch a lot of shared data, as you can see, right? In this particular case, we touch 6 shared data nodes, while we touch only 1 private data node. So in this case, keeping these 6 in the cache always, as opposed to ping-ponging a subset of them, is probably better than keeping the private data in the cache. Right? So this is a case where communicating the private data or keeping the shared data, the benefits of keeping the shared data on the large core outweighs the downsides of communicating the private data. But of course, this is not always the case. If you're adding a huge thing and your shared data is small, then there could be differences. Okay, so basically cache misses reduce if shared data is great, or touch shared data. The shared data that you touch is greater than the private data that you touch. Okay, this problem actually can be solved. We're going to see that. There are actually interesting things that can happen. It actually becomes a more general problem, as we may see, depending on the time. I'm going to talk about that paper. Actually, I really like this paper. This is actually applicable to, I think, a lot of communication that happens across threads. So hopefully we'll get to it. Okay, let's take a look at the performance. Yes, please. Yeah. Mm-hmm.
Depending on the workload, you choose whether you want to share that data or share data.
You mean ship the critical section or not ship the critical section? Yeah, potentially, yes. I think if you understand your workload, well, potentially. Yeah. And we're going to kind of see that in the next work. We're going to try to really identify what should we really ship to the large core. In this case, we blindly ship all of the critical sections except for the false serialization hack, let's say, that tries to fix a problem. But in the next work, we're going to really be more methodical about what should really be shipped there. We're going to collect more information about critical sections. And you could also do more, as you will see. Okay, so let's take a look at the results. So this requires a lot of simulation. And Onur, who did this work, which is part of his thesis, did a lot of simulation. It's not easy simulation in general. So basically, we're going to compare to this symmetric small core processors, an asymmetric multi-core processor that looks like this. We've already discussed this, but large core here in the ACMP, large core executes the serial parts of the code, but not the critical sections. Serial part is accelerated over here. Here in accelerated critical sections, ACS, large core executes both the serial parts, because that is actually good, as you will see in the results in general, and also accelerates the critical sections with the mechanisms we discussed. As I said, it's simulator development actually takes a lot of time for this sort of work. And you can see more in the paper, but these are the large core versus small core parameters. We kept the frequencies equal, but that doesn't need to be the case. But the main benefits of the large core is essentially large caches and also large instruction windows. And there's an on-chip interconnect that you need to model nicely. Okay, and we have 12 workloads that are critical section intensive. Okay, so let's take a look at these results. So it's always important to classify your workloads here. There are some workloads where the programmer was lazy, let's say, or the programmer was a regular programmer. And there are some workloads where the programmer was less lazy, meaning here you have coarse grain locks. And here you have fine grain locks. Fine grain locks are always harder to do because you run into the problem of debugging, etc., and getting it right. Coarse grain locks, you start your program, you write it, you lock everything, and your entire program is a single critical section. That's the laziest programmer. Terrible idea, of course, right? Even that you can parallelize in hardware. Like later, probably not today, but maybe in later lectures, there's this nice idea of speculative lock elision, speculative parallelization. Basically, the idea is programmer was probably conservative when they actually placed the locks. So in hardware, let me speculatively execute the critical section. It's kind of like run-ahead execution. When you see a lock, don't stop, checkpoint the architectural state, and keep executing. But not exactly run-ahead. The goal is not just prefetches. You could also do prefetches with run-ahead. But the goal is to really buffer results. And after you execute the critical section, if no one really conflicted with you in the critical section, just assume that you executed everything in the critical section. That's the idea. That's called speculative lock elision. It's a beautiful idea, I think. It adds complexity of speculative execution, more than run-ahead execution, actually, because you need to keep the results buffered, etc. But even if you have a conservative lock, you could actually accelerate this. Accelerated critical sections does something different, and there are actually trade-offs between the two. Okay, so I've given you some other ideas you can see, right? You can read the Micro 2001 paper on that topic, speculative lock elision. So let's take a look at the results over here. Here we're going to look at a chip area of 32 small cores. SCMP, symmetric CMP is 32 small cores. ACMP is 1 large and 28 small cores, basically. So you lose some parallel throughput with ACMP, of course, and also with ACS. But the overall, especially on programs that are not optimized, and also I should also say that this is really important. We have equal area comparison, but for each system, like the baseline, and when you accelerate the sequential kernels, and when you accelerate the critical sections, we pick the number of threads to be the best number of threads for a given system and a given workload. Meaning, for example, the number of threads that is best in the baseline system may be 5 for a workload, even though you have an area 32. Because the workload is not scalable in the baseline, right? If you actually, whereas the number of threads with ACS could be 10, right? That's the best threads. Now, if you compare both of them at 0.32, meaning if you actually execute 32 threads in each, the performance improvements of ACS is actually potentially much larger. But that's not necessarily a fair comparison, right? I mean, you could argue what's fair and what's not, because now you need to pick the best threads in a given system, which may be a difficult problem, as later works and previous work showed. So this is what we did for fair comparison as much as possible. And I'm going to show you some scalability results that show that. So basically, if your workload is not optimized, if you have a lot of coarse grain locks, you get a lot of benefits over here. So the light blue bar or turquoise bars over here show this acceleration of the sequential part, like the serial bottleneck. So you get a lot of benefits even by accelerating the sequential part, right? On average, not a lot, but there are some workloads that gain a lot. And there are some workloads that lose slightly because you lose performance on the parallel part. And these are actually more parallelizable than others. But accelerating critical sections buys you a lot more performance on top of accelerating serial parts. So that's good, hopefully. But you can see that the benefits are lower if the program has fine-grained locks, but they're still not negligible. So there are some workloads where you get about 20%, for example. And these are some online transaction processing workloads like that use database type of things. Okay, so I think I covered a lot of this, and I've already covered this one also. Okay, so these are the scalability curves, which are also interesting. I will not go into a whole lot of detail, but essentially you have the number of threads on the x-axis and the speed up compared to a single thread, single small core version, as you can see. And you can see that, let's take a look at some examples. Here's one example over here. In this workload, ACS, accelerating critical sections, shifts the curve to the right, meaning you get much higher performance, and the number of threads at which the performance becomes the highest changes, right? Your scalability improves. But still, you lose performance as you keep adding more threads, right? So the performance comparison points we have is probably here versus here. So the best points on each curve. That's what I meant earlier. Okay, here there are more interesting threads. So here, as you can see, we improve scalability significantly. For example, let's take a look at this OLTP workload. Baseline SCMP, symmetric multi-core, and ACMP look like this, look very similar. ACMP is slightly better by accelerating sequential bottlenecks. And here, performance keeps improving, as you can see, which is nice. And as I said, the comparison point is from here to here, as opposed to here to here. Does that make sense? This is the fair versus unfair comparison. We could have easily reported a much higher result by saying, okay, everybody executes 32 threads. But that's probably is not what you want to do if you actually are trying to optimize your program, right? Okay, so I could go over this, but essentially scalability improves in 7 workloads over here. In some cases, these programs are not that improved, as you can see. Okay, so I've already said all of this, so I'm not going to go through this. Essentially, we can improve both performance and scalability by accelerating critical sections. And these are critical sections. Now we're going to generalize the idea. Because critical sections are only a part of the bottleneck, right? Can we accelerate all bottlenecks, or ideally critical paths, by executing them on a powerful core? I think in the ideal incarnation of the idea, which is not going to be the next paper is going to move the needle compared to the previous one, but it's not going to identify all possible critical paths. Because I think there are critical, ideally you would like to do this for even a single-threaded program, right? If you have a single thread, you figure out what is my critical path, and maybe accelerate it in some specialized core, maybe a large core, maybe more specialized core. It's good to think about that, basically. But we're not going to do that for single-thread programs yet. Okay, so this is the paper. You can read more about it. Let's talk about generalization, unless there are questions. Yes? So in water, do you know how TCuARCH yeah. Yeah. Decide. Yeah. Yeah, that's true. Yeah, I think it's not easy, basically. You have, basically, it depends on what workloads you're targeting, but these are general purpose cores. So they're normally targeting quite general purpose workloads. Essentially, I don't have a good answer because I don't think anybody has a good answer on this one. You run a bunch of, normally the way general purpose design happens is you have a target set of workloads, which is quite diverse. You run traces, for example, you collect traces from your customers, you add your traces that are from benchmarks. For example, there could be easily thousands of traces in your trace set or workload set. And you do some design space exploration based on those traces. You run all of those traces and you try to figure out what kind of performance, what kind of energy you get. And that's very intensive to begin with, right? You need to simulate things. You cannot really run them on real hardware. So people have actually designed simulation clusters people use simulation clusters to do this sort of simulation. And then you still have limited design space exploration in the end. That's why you need to use some intuition. But here, intuition may not help easily also. So if you look at those pictures, I think Apple had 16 high-performance cores versus 8 small cores. Sometimes it's just also area constraints, right? I have enough area, so let me add more. This also is a little bit this sort of data-driven exploration is also not necessarily representative of what workloads are going to be executed, right? Because you're looking at past workloads to design an architecture for the future. And the future architecture may be executing completely different workloads, right? Parallelization patterns may be different, etc. So there's no perfect way, unfortunately. It's a combination of methodical simulation plus intuition plus some luck. Yeah, that could be said of all architectures probably. But some problems are easier, yes. Okay, so the next, unless there's another question, let's talk about how we accelerate all types of synchronization bottlenecks. And I think we really tried to cover all here. And I believe all types of synchronization bottlenecks can be expressed with the framework that I'm going to describe. And this is the paper. It's called Bottleneck Identification and Scheduling. I've already said a lot of these. Essentially, any code segment for which threads content could be described as a bottleneck in a multi-threaded scenario. In a single-threaded scenario, this is actually broader, right? Because there's no thread contention, right? Now you need to talk about critical paths, etc. Basically, any code segment that makes some thread wait, this is identified as a potential bottleneck. Serial portions clearly make everybody else wait because there's nobody else. Only one thread exists. This is on the critical path by definition. Critical sections that ensure material exclusion, they're likely to be on the critical path if they're contented because they make some folks wait. But their severity may depend on how many threads they make wait for how long, right? Not all critical sections are equal because some critical sections make no one wait, right? If the critical section gets executed and no one is contending for it, sounds great. That's what speculative lock collision exploits, right? Critical section executes, no one contends, so you don't need to do any waiting. But actually, what speculative lock collision exploits is two critical sections execute the same critical section, and there's no conflict between them. One of them is modifying this part of the tree, the other one is modifying this part of the tree, and in the end, if you execute both of them concurrently, you'll get the correct result, right? But the programmer needed to be conservative because programmer didn't know that. Yes. Yes, when we talk about that, essentially you check whether you get a data conflict if someone requests the data that you updated or read. You can check that in a real processor through coherence messages. That's how they did it in that paper. Okay, we can talk more about it when we discuss coherence, etc. Okay, so that's critical section. Barriers, we've all seen barriers. Essentially, they ensure all threads reach a point before continuing. The latest thread arriving is on the critical path of the barrier. And once you fix that critical path, there could be another latest thread arriving to that. So you could actually, barriers are interesting also. And finally, pipeline stages, we've seen that also. Different stages of a loop iteration may execute on different threads. And slowest stage makes other stages wait. And that is on the critical path. So basically, we want to identify those code segments that are on the critical path in multi-threaded programs. There's also one more thing over here. These bottlenecks can change over time. So this is let's say, cooked up example that Jose developed. Jose led this work a while ago. Essentially, whenever you come up with a cooked up example, you'll find versions of it in real code. These things exist. So come up with a cooked up example and you'll find some type of code that exists in real life. But in this cooked up example, we're going to look at copying data from a full linked list to an empty linked list. Essentially, what we will do is we're going to lock the list A, which is initially huge, populated a lot. You traverse the list and remove X from A, and then unlock it, and then do some computation on X, and then lock list B and move data or copy data from B to, copy data X that you've updated into B. Essentially, you insert. You do a removal operation from a shared list A and an insertion operation for a shared list B until A is empty. So you can see that this is kind of a cooked up example, but it's a nice example also. And all of the threads are going to do this. And these are different critical sections, clearly. Now, the purpose of this was to show that critical sections change, bottlenecks change over time. So this is the time of execution with some input data. I think there are maximum 32 threads over here. And this is contention, number of threads waiting for the critical section, blue one versus red one. As you can see, initially blue one is very contended, but as you keep removing things from the blue one, the contention over here reduces because the size of the thing reduces. And after some point, the red one becomes contended. So there's a part where both of them may be contended, and the red one becomes less contended after some point also because you're adding less stuff. So as you can see in this example, lock A is the limiter for some time, lock B is the limiter for some other time, and then there's some area, some time where both of them could be limiters to different degrees. Okay, so that's just a cooked up example. Here is the real example from MySQL, which is actually more complicated. We're just looking at 2 locks over here and 16 threads. And we're looking at how many threads are waiting for each of the locks. And this is a fine grain, as you can see. It's millions of cycles. You can see that there are some points where the red lock is contended a lot. There are some points where the blue lock is contended. And there are some points where both of them may be contended to various degrees. Okay. So the goal is to adapt, essentially. You cannot say a critical section will be critical for good, for long. So the key insight here is actually very simple. We're going to go to the fundamentals. Fundamentals, what causes thread waiting is not good. Because thread waiting is probably loss of parallelism. If a thread waits, that's not good. It reduces parallelism and is likely to reduce performance. And the other intuition is that code causing the most thread waiting is likely on the critical path. This is not always the case, of course, but this is a heuristic that we're going to use to decide what code to prioritize to accelerate. You could use different things, of course, as we will see. So the key idea here is dynamically identify the bottlenecks that cause the most thread waiting and accelerate them. In this particular case, we're going to use powerful cores in an asymmetric multi-core processor. But you could actually do other things, as we will briefly discuss. You could, for example, increase the frequency of the core that's executing this bottleneck, right? And if we get to it, clearly there are benefits of that, right? So you don't move the code somewhere else, but then you lose the benefits on data and shared lock, etc. Basically, you can do other things. Assuming you identify bottlenecks that cause the most thread waiting, you could do other things. Keep that in mind. So in this sense, this work is a bit more general framework. It's not saying just accelerate every critical section on some other core. It's basically saying identify the bottleneck and do something about it. Okay, so how are we going to identify the bottlenecks? That's a key question over here. So we're going to do, again, a hardware-software cooperative approach. Compiler, library, hopefully not the programmer, but if they wish so, the programmer can annotate the bottleneck code, and we will see what kind of annotations we use, and they're going to implement waiting for bottlenecks. This implementation of waiting will count, essentially associate a counter with each bottleneck, and that counter will count how many waiting cycles that this bottleneck causes for different threads. And then there will be a binary containing these BIS, bottleneck identification and scheduling instructions. And in hardware, when that binary gets executed with the annotated code and waiting implementation, the hardware will measure the thread waiting cycles for each bottleneck and dynamically figure out which bottleneck caused the highest thread waiting cycles and accelerate that. Okay, so it's a nice framework. Unfortunately, it requires changes to both hardware and software, as you can see. Let's take a look at the software changes. So this is a critical section. We try to abstract away as much as possible. So while you cannot acquire the lock, you wait for, essentially, we wait by watching an address. And then you acquire the lock once you're done waiting, and then you release the lock. Right? Now, we're going to outline this call. You don't necessarily have to, but for making things easier, you outline it using a bottleneck call. Essentially, bottleneck call, we're going to associate a bottleneck ID with each critical section. And we're going to call the bottleneck, and then the code remains the same. And then we're going to do a return, bottleneck return. Sounds nice, right? This way we can identify, we can give an identification for every single bottleneck in a program. Okay, that's the bottleneck ID. Now we need to do something else. This is not enough. Bottleneck call, whenever you get to a bottleneck call, now you can say, oh, I'm going to call a bottleneck. Do I think it's critical at this point, right? So this can enable acceleration clearly. But where is the input for the do I think it's critical? And that will come from this side, basically. Bottleneck return, of course, assuming you accelerate it, now you can actually return the bottleneck, etc. So those are easy, hopefully. This is the part where we're going to change. While a thread is waiting for this bottleneck, it cannot acquire the lock. It's waiting for BID clearly. We're going to basically increment a counter in hardware. There's a specialized instruction called bottleneck wait. While you're waiting for that address to be modified, because that's the synchronization that happens, you increment the thread waiting cycles for that particular bottleneck. So now we have changes to the instruction set to enable this. This is used to keep track of waiting cycles, and these are used to enable acceleration. Sounds good, right? And this simple mechanism can actually be used for not just critical sections, but also for barriers. This is an example where you have a barrier. A little bit more complicated, but again, if you look at the code, it's not that bad. In the paper, we have the basic code and then the change code. But essentially, you have a bottleneck call for the barrier. Here, there's a code running for the barrier. This is basically everybody executes this code, different threads. And when the barrier ends, you do a bottleneck return, right? So this is really the parallel portion of the code here. Now, once you're done with the parallel portion, you return and you enter the barrier. This is the really waiting part. And if not all the threads are in the barrier, you're really waiting. So the thread that is executing still is really exercising this bottleneck. This way you can identify the bottleneck. And the paper discusses more on how to handle barriers. I'm not going to talk more, but you can actually handle. Okay, that's barriers. This is pipeline stages, which is also, again, using this framework. You have a bottleneck call. This is really the pipeline processing. In a pipeline processing, you have an input queue and you have an output queue. You check your input queue first, get some work. If your input queue is empty, maybe you're running too fast compared to the previous pipeline stage that's supposed to be feeding you things. So you're really waiting for the previous bottleneck ID. Right. Now you do the work, assuming you get some work over there, you do the work, which is the parallel part. And you check whether the output queue is full. If the output queue is full, then you're again probably running far ahead from the thing that's waiting the results from you. Because if it was actually matching your throughput, it wouldn't have a full queue, right? So basically, the next bottleneck is your bottleneck. So you're waiting for that bottleneck now. Clearly, you could be waiting for both at different times, right? So that's the idea. This is, I think, it's a beautiful framework to really mark instructions this way. Okay, so now we've annotated this. Let's take a look at what the hardware does. With this information, the hardware can do a lot actually. As I said, identification and acceleration are independent tasks. Acceleration can be accomplished with different ways. You can increase the core frequency voltage of the code that's executing, of the core that's executing the bottleneck that's identified. You can prioritize that bottleneck in shared resources, as we have seen actually in not thread cluster, but parallel application memory scheduling. These works are actually done concurrently. So prioritization in shared resources, you can prioritize a thread in the memory scheduler that is executing a bottleneck, for example. And you can migrate to faster cores. You could actually do a lot more, I think, but it's not limited. You can imagine things. So we're going to migrate to faster cores. Let's take a look at this. How do you measure thread waiting cycles for each bottleneck? I'm going to give you an example. You have 2 small cores, 1 large core. We're going to add a bottleneck table. We're going to modify things a little bit. This bottleneck table is going to keep track of how many thread waiting cycles each bottleneck has caused. So small core executes a bottleneck wait for a given bottleneck ID. The waiter count gets incremented, and thread waiting cycles gets counting until this small core stops waiting for that bottleneck. Okay, so you keep counting basically, as long as you have a waiter for that bottleneck. You can implement in various ways, it's not that hard. Now, you keep counting. Now another core starts waiting for the bottleneck, same bottleneck. You increment the number of waiters, and you keep counting, incrementing the thread waiting cycles by twice every cycle. You could, of course, quantize things, etc., which the paper does, but I'm not going to go into that. Once a core stops waiting for the bottleneck, it basically notifies the bottleneck table saying, I'm not waiting for it anymore. So that decrements the waiters count. And then you go back to counting in a different way. And once the other core stops waiting for the bottleneck, this gets communicated again through the interconnect to a bottleneck table, which is located somewhere closer to the large core in our implementation. And then now the number of waiters is 0. Right? Now this way you can count the bottlenecks because you annotated the code so that you can keep track of the bottlenecks. It's nice, it's expensive. I mean, not cheap, clearly, but it's doable. Okay, now how do you decide what to accelerate? Now you assume that you have some thread waiting counts, which may be periodically reset, etc., which I'm not going to go into again. But you have multiple bottlenecks. One of them clearly has caused more thread waiting cycles than the other one. And small core gets a bottleneck call to 4600. Right. The first thing it does is it queries this bottleneck table asking, should I execute it or should I send it somewhere? And the bottleneck table coordinating, it says basically, oh, that's not an important bottleneck. Go and execute it yourself, right? Don't bother me with it. So execute locally, right? And then it gets another bottleneck. This time it's 4700. Again, it's asked the question, should I execute it myself or should I send it somewhere? And the bottleneck table says, this is important. Let me handle it in the large core. Right? That's the idea. And this way, of course, it's not that easy. Basically, it tells a small core to execute remotely. And remote execution is very similar to accelerated critical sections, basically. You need to execute, you need to send the things related to the bottleneck. Now, similar to accelerated critical sections, we have a bottleneck scheduling buffer in the large core. It gets essentially the bottleneck ID, program counter that it should start with, a stack pointer because the communication is done again through the stack between the thread private data and shared data in the bottleneck, and also the core ID so that this large core can tell when it's done, you can stop waiting, right? At some point, this gets scheduled on the large core. And then large core executes the bottleneck return. Remember that bottleneck return instruction we added, which sends a signal to the core ID that initiated that bottleneck, and small core can stop waiting. Hopefully that makes sense, right? Of course, this bottleneck table becomes a bottleneck itself, at least in the communication. So what we do is we try to make the decisions locally. You don't want to go to somewhere else to decide whether you execute locally or remotely. So we add essentially cache of parts of this bottleneck table. Whenever the bottleneck table identifies that a particular bottleneck ID should be accelerated remotely, it sends a message to all of the acceleration index tables saying that this should be accelerated remotely. Meaning the default is local execution unless you find it in your acceleration index table, right? This way you don't need to communicate too much, hopefully, with the bottleneck table. And that reduces the bottleneck table from becoming a bottleneck by itself. Okay, sounds good, hopefully. So basically, we've discussed both of the mechanisms, basic mechanisms, thread waiting cycles, accelerating bottlenecks. But there are also other things that you need to improve, the performance and generality of this. In the paper, we talk about that. I'm not going to talk about these in detail, but dealing with forced serialization is still a problem. There's preemptive acceleration that's important for especially barriers, and I'm not going to talk about that. Barriers need to be more preemptively accelerated. Critical sections, depending on the history, you can accelerate them later. But barriers, while the barrier is executing, your bottleneck things are essentially bottleneck wait cycles are accumulated, and there's a thread that you need to determine that's the latest, right? So you need to preemptively get there. And there's support for multiple large cores. So in this case, we actually added support for multiple large cores so that we can accelerate things, multiple bottlenecks in parallel. Hardware cost is in the paper, and I'm not going to talk about this in detail again. It's not that much. Everything is off the critical path, especially after you design the bottleneck table the way we think with caching using acceleration index tables. So the total storage cost is not a lot, but there's complexity, of course, right? Okay, again, you have trade-offs over here, which are very similar to ACS. So I will go through this relatively quickly. Now we have faster bottleneck execution versus fewer parallel threads. You have better shared data locality versus worse private data locality. We're going to solve that problem in the next work. And you have benefit of acceleration versus migration latency. Right? Okay, so we've already, I think I should actually mention this one also. Migration latency is usually hidden by waiting, meaning you migrate, but then because if something is a bottleneck, it should wait. It should not wait unless it should not wait if the bottleneck is contended, right? Basically, migration latency is not hidden if you're not going to wait on this bottleneck. But this is bad, of course, but this is likely not on the critical path. And assuming you're doing your accounting correctly, hopefully you have not migrated, right? So that's the interesting part over here. By doing this accounting better, ACS, accelerated critical section, accelerates everything, right? Here, we basically do some accounting, and based on that accounting, we actually decide to migrate. And I think overall, migration latency is reduced significantly. So this idea is actually more general. We've talked about speculative lock collision, right? One of the issues with speculative lock collision is deciding whether you want to actually speculatively execute a critical section. In some cases, this is a very bad idea because the critical sections are going to contend with each other. And when the critical sections actually contend with each other, you run into a situation where you go back and serialize everything. So you have to recover. So if you can actually identify whether critical sections are actually going to contend with each other with this sort of mechanism, you can guide this lock elision in a much better way. So you can speculatively execute critical sections in a much better way. So this, in that sense, this mechanism is actually a framework that can enable better parallel execution. Okay, so we evaluated this again using a bunch of workloads. These are other workloads that we added to the suite. And again, we have large cores or small cores. You can read more about them. These are the comparison points. So asymmetric multi-core, we already discussed that. It accelerates serial portions, and there's accelerated critical sections. And then there is something else called feedback-directed prefetching, which is applicable to pipelining. So critical sections, accelerated critical sections was not applicable to pipelining. And feedback-directed pipelining here, actually, it's a nice idea. The idea is actually, in software, identify which pipeline stage has the lowest throughput. And if it has the lowest throughput, accelerate it in a large core. That's the idea. It's applicable only to pipeline parallel workloads, not to critical sections. Of course, a workload can have both pipeline parallelism and critical sections. In that case, these ideas are applicable together, of course. Right? Okay, but we're going to talk about that also later, hopefully. So this is the performance improvement you would get. On these workloads, ACS, accelerated critical sections, and feedback-directed prefetching buy you performance, which is good, which is actually similar to what we have seen earlier, but maybe we have more improvements in the baseline here. And if you do bottleneck identification and scheduling, you do better. And there are some workloads where you don't get a lot of performance. And then there are also workloads where ACS is dominantly applicable versus feedback-directed pipelining is dominantly applicable. So there are a bunch of workloads where limiting bottlenecks change over time that we have identified. And here, BIS actually provides a lot more improvement. And here you have barriers where ACS cannot accelerate, which is interesting. Okay, these are the results. I will not go into more detail. And it improves scalability on 4 of the benchmarks, which is not shown here. Now, there's also more analysis, which is actually a very interesting analysis, I think. It's good to do this sort of analysis. We wanted to understand why does it work, meaning we wanted to analyze the fraction of execution time spent on predicted important bottlenecks. And this is what this shows. This is easy to get. This part is easy to get. ACS or FDP, the fraction of you can also see this as the amount of time the large core is busy doing something. you can see that if you accelerate only critical sections or pipeline stages, that fraction is relatively small, especially with critical sections, right? Because most of the time there is not something that the core is not in a core is not in a critical section. With BIS, that fraction increases in general, not always. Meaning we keep the large core busy more, right? Okay. What fraction of that is actually critical? I mean, one of the reasons we keep the large core busy more because we ship more than critical sections to the large core, right? Not just the critical sections. We're more frugal in which critical sections we ship, but we also ship other stuff to the large core. But you can see that the large core utilization is still not 100% in many cases, or not even close to 100%. So there could be more done on the large core, as you can see. Now, what fraction of this is actually critical? This is a much harder question to answer because you need to somehow figure out, okay, you execute something. Is this really critical? Is this really on the critical path of a program? This analysis is actually very difficult. It needs to be an offline analysis, and it cannot be a perfect analysis because of the dynamic nature and dynamic changes on the critical path. But if you do some sort of analysis that is close enough, we define coverage as a fraction of program critical path that is actually identified as bottlenecks. And that increases from 39% to 59%. So it's these green bars over here. So we identify a larger fraction as bottlenecks, which is probably good because there should be some bottleneck in the program, hopefully. And accuracy is the identified bottlenecks that are on the critical path over total identified bottlenecks, which is basically total identified bottlenecks is this blue bar, and the green bar's fraction is about 72%. With bottleneck identification of scheduling, we increase coverage while keeping accuracy almost the same. Okay, that's the best we could do with the accuracy analysis. It may not be very easy to do this analysis. But basically, the takeaway is that we can identify 60% of the program critical path as bottlenecks, and about 70% of that identification is correct, which means that we're still leaving a bunch of stuff on the table, right? You can multiply 60 by 70, you get about 42%, right? Some of the things that we're shipping is identified incorrectly as the program critical path. So we're wasting resources. And some of the things we're not even identifying well. Okay, it's good to keep this in mind. So we have a bunch of more results. So as you have more small cores, you get better performance because contention increases and loss of parallel throughput reduces. I'll not go through this. If you have more large cores, it's actually good because you can accelerate independent bottlenecks without reducing parallel throughput because you normally have enough cores for parallelism. And also you can do multi-threading. Okay. So I think we have covered this. Essentially, I think I will probably say this last point over here. This is a mechanism that gives you fine-grained bottleneck acceleration with no programmer effort. Hopefully no programmer effort. If the programmer programs libraries, you could actually do all of this in libraries. You could design a library, locking library, barrier library, pipeline parallel programming library that the programmer uses, and all of these instructions are already compiled, right? That's ideally how it should be. But if the programmer tries to do a lot of tricks in the low-level code, then clearly this is not going to work. But if they're doing tricks in the low-level code, maybe they can add these tricks also to the low-level code. It's good to think about that. And this gives you a more finer-grained bottleneck acceleration with hopefully no programmer effort. Okay, I think I've covered this. This is the paper. There is an improvement over this, making better acceleration decisions. I think I'm not going to cover this. I'm going to let you study it on your own. This is utility-based acceleration. The basic idea is I'll give you the basic idea, and then we're going to end early today, but I can take questions. The basic idea is to identify the utility of acceleration. Here, we made an acceleration decision based on thread waiting cycles, right? And then the next question is that good? Because we're using thread waiting cycles as a proxy for identifying a critical path. But maybe there's something else. So if you can identify each code segment, associate a metric with a code segment, saying this is the performance improvement I would get if I actually ship this code segment to the large core, that's really what you want, right? And this is what we try to approximate in this work. I'm not going to talk about this right now because we've talked a lot. We may start with this tomorrow, or I may leave it for you to study on your own. But we're going to continue this lecture tomorrow. Any questions? Yes. Hmm. Yeah. Yeah. More large cores. Yes. Yeah. I mean, these works, that's true, but we also evaluated more large cores. So we basically always said that if you have more area, you can also put more large cores. Yes. So I think in the end, if you have area, so when we were doing this work, it's like 2008, 7, 8, because of multiple rejections of the papers. The first paper was published 2009. It was rejected 4 times, I think. But basically, 2007 and 2012 timeframe. At that point, we didn't have that many transistors. Right now, I think because there are so many transistors, people can afford to put more large cores, for sure. And also, I think examining multi-threading, because today multi-threading is relatively common in large cores. Maybe not huge levels of multi-threading, but 2, maybe 4. So examining multi-threading together with large cores is useful, I think, in these. Hopefully that answers your question. Today, people do it because they can. And some workloads benefit, actually. Yeah. Any other questions? Yes. Okay, can you speak up? I cannot hear very well. Okay, we've shown examples of this in prior lectures also today, but a critical section is a part of code that enables mutual exclusion, meaning if only one thread can be executing that code and no other thread. And the main reason to have a critical section is to protect shared data, to do updates to share data accurately. Yes. Hmm? Hmm. Hmm. That's right. Hmm. Yes. So what we ship is, let me go back. I'm going to go very quickly. We actually ship the actual instructions that make threads wait. So maybe that was not clear, but basically you can see that bottleneck call, this is really the code running for the barrier, meaning the parallel part of the code. Does that make sense? Hopefully that clarifies it. But barrier instructions are really here. You enter the barrier, and this is where you actually do the synchronization. But this is really the parallel part of the code. That's right. That part, assuming this bottleneck is identified as a bottleneck, that starts getting shipped to the large core. The parallel part gets shipped. So in that sense, bottlenecks, barriers are a bit different. But also pipeline stages are also a bit different because you also ship the large part to the pipeline. Essentially, in critical sections, the critical section gets shipped. In barriers, the parallel part until the barrier gets shipped. And in pipeline stages, the code in the pipeline part gets shipped. Yeah, but barriers are a bit tricky that I didn't want to go into. There's also some preemptive acceleration that you need to do because what happens, you already entered the barrier and you want to essentially, and you get identified as a thread, right? That is bottleneck. What do you do in that case? You're running on the smaller core. So I'll let you think about that. So you need some more software modifications to indicate like which threads are running behind. Yeah, or you need higher level software constructs, meaning this is the work that's assigned to me, and this is the amount of work that I have accomplished. And that's a measure of progress. Basically, you need a measure of progress for threads. Yeah. Barriers are interesting. Okay, any other questions? I wanted to end early, and we'll end a bit earlier. Okay, I'll see you tomorrow. So just to jog your mind, we covered heterogeneity yesterday. We're going to cover more of that, but our focus will be a little bit on bottleneck acceleration. These are some of the readings that we were covering, and we were talking about asymmetric multi-core, and these are some papers we covered. So we started with accelerating critical sections. We actually started accelerating serial bottlenecks and put them on a large core, which made things faster. And then we accelerated critical sections kind of blindly, put them on a large core, which made things faster. And then we kept asking the question, can we generalize this to all types of synchronization bottlenecks in multi-core, in multi-threaded applications? And we came up with a solution, bottleneck identification and scheduling. And that made things faster for different types of bottlenecks, as we have discussed yesterday. And that was the paper. And we also asked the question yesterday at the very end, can we make better acceleration decisions? And I mentioned very quickly that you could actually take into account utility. I will not go into detail over here, but I will show you something that we briefly discussed yesterday. So we were talking about bottlenecks, right? This is a parallel program. A parallel program may look like this. In between barriers, you may have different critical sections that look like this. The red parts are critical sections. This is one way of one type of program. You may not, you don't have to have barriers also, of course. But here the critical path goes through the critical sections, as you can see. And you can accelerate them. You can accelerate them better with the bottleneck identification and scheduling, as we've discussed. And then there's another bottleneck, which is really the barrier over here. And the last thread reaching the barrier causes a problem. And if you actually improve just that last thread a little bit, if you identify it too late, your improvements may not be very high. We kind of discussed this yesterday. So these are essentially different bottlenecks. So we've also discussed, actually here you can see that the bottlenecks are combined. You have some critical sections, and then you have a barrier at the end. So this last thread can be accelerated, and also critical sections can be accelerated together with it using the bottleneck identification and schedule. So we've discussed all of this yesterday. Both of them can be accelerated. Now, we've discussed also this, but we didn't go into a lot. I will illustrate it a little bit. There's actually more potential if you look into this sort of application. Maybe get rid of the critical sections. You have a box synchronous parallel program like we've discussed yesterday. And if you know how much work, how much progress is expected from each thread, you can kind of mark that progress. And you can identify a potential bottleneck much earlier. This is called lagging threads. It may be difficult to do. It really depends on whether you can correctly identify how much progress has been made by a given thread. For example, if you can somehow magically identify that processor 2 made only 30% progress in its task, whereas some other processors have made more progress, maybe you predict that that thread 2 that's executing on processor 2 is actually your bottleneck. And you can somehow accelerate it. Well, we know how to accelerate, right? You can ship that to the large core, for example, right? So this is something that is discussed in the papers, but I'm not going to talk about that in detail. But you can also identify lagging threads, essentially, so that you can optimize this execution until the barrier much more nicely, until something really becomes a limiting bottleneck. Does that make sense? Basically, it's more progress determination, right? Okay, so the question, of course, becomes, there may be many of these things that happen at the same time in a program. Do you accelerate the bottleneck or do you accelerate the lagging thread, right? And in a program that kind of looks like this, you can have both of them. You may have bottlenecks in critical sections, and you may actually identify a lagging thread also. In this case, they're probably the same, but in some other cases, they may not be exactly the same, right? So that's one question. So things become more complicated. And then things become even more complicated if you have multiple applications, right? Which application do you accelerate? So far, we have not talked about multiple applications in this bottleneck accelerating lectures, even though we had talked about them earlier when we talked about resource sharing a lot. Now we're going to kind of combine both, although I'm not going to go into a lot of detail over here. Basically, you may have two applications that look like this. One of them may have a critical section as a bottleneck. Another may have a lagging thread or a barrier as a bottleneck. Then basically, you need to make a better decision than what we have done before. Actually, we didn't have a mechanism for making a decision before. Who uses the large core becomes interesting. If there are multiple large cores, of course, maybe you send two things to different large cores. But then as applications increases, the number of applications that may be demanding the large core may be more than the number of large cores that you have. So in the end, acceleration decisions, better acceleration decisions, probably need to consider both the criticality of a code segment, how important that code segment is, and how much speed up can you get by accelerating that code segment. Both of these are important. If the code segment is not critical for performance, maybe accelerating that is not going to buy you much. If the code segment would not get performance, higher performance, if it gets shipped to a large core, then maybe it is not worth accelerating that much, right? So this paper takes a methodical approach for both bottlenecks, different bottlenecks that we've examined, plus lagging threads for any running application. I will give you the basic idea, and I like this approach, actually. It's a very methodical approach. I believe this sort of approach needs to be applied for other things. In later works, we have applied it to hybrid memory management. Basically, we developed a utility-based hybrid memory management technique that considers utility of moving a page from slow memory to fast memory in terms of how much benefit you would get. So we're going to do something similar over here. Basically, our goal is to identify performance-limiting bottlenecks or lagging threads from any running application and accelerate them on large cores of an asymmetric multi-core processor. But of course, you can have different methods for acceleration, as we discussed yesterday. And this paper introduced a utility of acceleration metric that combines speed up and criticality of each code segment. I'm not going to tell you exactly how this is computed. Otherwise, we would take a long lecture on a single paper, which I don't want to do today because we have a lot of other fundamental things to cover. But basically, the basic idea is it breaks down things in an easier to compute way, because this utility of acceleration may not be directly easily computable, but pieces of it may be computable. Essentially, we define the utility of accelerating code segment C of the length T on an application of length large T as a combination of these three things, which kind of look funny, right? But basically, if you really understand what's going on, this is the local speed up that you would get by accelerating that segment on a large core. This is the fraction of execution time that's spent on the segment, the importance of the segment for the application. And this is the global criticality of a segment, essentially, which is a more global measure of what's going on in the machine. And there are different ways of estimating each of these, which I'm not going to go into, but I like this methodical approach. And if you do that, basically, there are two things that this paper does. It identifies bottlenecks, and it selects a set of highest utility bottlenecks. It identifies the lagging threads using a different mechanism. Bottleneck identification is done exactly like we did with bottleneck identification and scheduling. Lagging threads adds a little bit more sophistication because you need to really understand how much work is assigned to each thread and how much progress each thread has made based on that amount of work, which may not be completely accurate. And once you understand once you have a set of highest utility bottlenecks and highest utility lagging threads, there's a coordination mechanism that decides which one to actually send to the large core, assuming you have a single large core. If you have multiple large cores, the problem becomes a little bit different. But again, you can still find out which ones are the highest utility bottlenecks and lagging threads, and then decide how many cores to use for them. Does that make sense? I wanted to cover this. Yesterday, I said maybe I shouldn't cover this, but I had to cover it because this is really the state of the art and on identifying. Did I do something? On identifying bottlenecks. And also, it's a methodical approach, right? It's a more methodical approach to understand the benefit that you would gain from acceleration. And the results are actually reasonably good. These are the comparison points. Essentially, there's a multi-program aware bottleneck identification and scheduling. That's the red bar. That's what you've seen yesterday, plus some multi-application awareness. And there's another work that does performance impact estimation that's around the same time. And compared to both of those approaches, you get higher benefit in most applications. This is an S-curve, as you can see. These are about 55 workloads over here. And usually, whenever you actually evaluate a mechanism and compare it to some baseline, in this case, actually, I don't remember what the baseline is, but I believe it's ACMP in this case. It may be ACS, I'm not sure. Don't quote me on it. It's in the paper. Probably it's ACMP. You see that some applications actually lose performance and some applications gain performance. And usually this is the curve you get. It's kind of like an S-curve. That's why it's called an S-curve, actually. The curve looks like an S. And you can see that overall, doing utility-based acceleration provides better performance, but not in all cases. So there's still room for improvement, as you can see. Make sense? Okay, so I think the sort of utility-based metrics are interesting and important to use. People have applied this sort of utility to cache partitioning. In fact, a paper won the best test of time award at Micro this year. It's called utility-based cache partitioning. In past lectures, when we actually talked about caches, we would talk about it, but we don't have lectures on caches probably this time. But if you're interested, you can look at that also. And later works also try to understand the utility of different decisions. So if you can somehow figure out the utility or performance benefit of making a decision and compare it to performance benefit of making other decisions, you can actually make much more principled decisions, I think. The question is how easy it is. This clearly is much more complicated than thread weighting cycles, right? Thread weighting cycles was easy. It's relatively easy to compute once you have the mechanisms in place to actually keep track of them. In this case, you need to keep track of a whole lot more. And that's true for any kind of utility-based metric. If you look at utility-based cache partitioning, there's additional hardware that you need to add that's more significant than keeping track of how much reuse you've had in a cache line, for example. If you look at utility-based hybrid memory management, which is also another paper in 2017, that also adds a lot more hardware. Okay, so the question is, of course, always, can we do better? But before that, maybe any questions on this? Okay, now we're going to tackle another issue, which is actually something that had been bothering us while we were doing a lot of this work. And the bothering part is really this private data locality that we discussed yesterday, right? What we do when we accelerate a code section is we keep the shared data and shared locks in the same cache, right? Because you accelerate that, at least the important code sections, on the large core. This is good. So you improve shared data locality, but this comes at the expense of private data locality, because now you need to transfer things that are produced by a thread locally and then consumed by this critical section or bottleneck on the large core, from the small core to the large core. So that's the issue over here. And this paper develops a mechanism for handling this nicely, I would say, which I think is actually a more general mechanism that we should think about in general. Because if you can keep the shared data in a single place and send the operations that work on the shared data to that place, you've solved that shared data locality problem as much. Now your problem really becomes, your bottleneck really becomes the private data. And I will show you some examples of that. And I think there should be more improvement in this direction also. So this is actually a very general problem. So I'm going to generalize the problem even more. This applies, I think, also to single-threaded applications, multi-threaded applications, any application in the end. So I'm going to introduce something that we call stage execution model. And I think the goal in essentially parallelism is to speed up a program by dividing it up into pieces. And the idea usually is you split a program code into segments. You may call it many different things: threads, tasks, dynamically formed tasks, etc., or critical sections. But we were going to call it segments in this particular case to be general. And your goal is to run each segment on the core best suited to run it, right? And we've kind of done that in earlier works. And one way of doing this is actually to have each core to be assigned a work queue, storing segments to be run. This doesn't have to be the case, but we're going to kind of assume that. You don't have to assume that in the end. The benefits you get, as we have seen in earlier works, is you can accelerate segments or critical paths using specialized or heterogeneous units. That's what we've seen in the last lecture. Clearly, you exploit inter-segment parallelism. Even if you don't ship it to a large core, the stage execution model, segmenting a program, buys you parallelism across different cores, right? That's the classical multi-threading. And if you actually try to run each segment, if you actually partition your program nicely, such that segments that operate on the same data are scheduled onto the same core, you can improve the locality of within segment data. And that's what we get with putting critical sections that operate on the same shared data to a large core, right? So you can get a lot of benefits, which is nice. This is actually, basically, if you look at these benefits, these are very fundamental concepts. Going from bottom to top, you get locality, you get parallelism, you get heterogeneity, right, or specialization. Now, there are examples of this. Clearly, we've discussed a lot of examples. Multi-threading is a very general example of it, but accelerated critical sections, bottleneck identification and scheduling, pipeline parallelism, producer-consumer that we've discussed. Other task parallelism models, these are old slides, so people have been using interesting task parallelism models. They're still in use, actually, to parallelize workloads. And special purpose cores and functional units actually can be thought about it this way also, because if you think about a single program, a specialized functional unit is really executing a segment of the program okay, maybe core should be more generalized also, on a functional unit that's specialized for the execution of it, right? So if you think about it, this model can be broken down into even smaller pieces than cores. We're not going to do that in this, but I think it's good to think about that. Okay, so let's take a look at the stage execution model. You have, assuming you start with a single program, I'm just showing you the loads and stores. You split, or someone splits the code into segments. It could be the programmer, it could be the compiler, it could be the hardware. Assume that programmer has done it. Now you have segment S0, S1, S2, and they communicate with each other. And maybe segment 0 communicates on the same type of data, right? You can think of it that way, some similar arrays. And then you communicate something to segment 1 and then something to segment 2. And then you assign instances of segment 0 to a core, instance of segment 1 to another core, instance of segment 2 to another core. And then you can hopefully exploit inter-segment parallelism, right? So this is one way of spawning segments. When you execute segment 0, when you get to the end, maybe you spawn segment 1 on core 1. You spawn segment 2 on core 2. It's going to be very similar to ACS very soon, right? But the pipeline parallelism is also kind of like this. Maybe you don't necessarily have a spawn instruction, right? Okay, so let's take a look at two examples over here, accelerated critical sections. The idea here is to ship critical sections to a large core in an asymmetric CMP, multi-core processor. You can think of segment 0 as non-critical section and segment 1 as critical section, right? Any critical section is segment 1, any non-critical section is segment 0. You can further classify different critical sections, of course, right? But this is the general idea. So the benefit you get is clearly a faster execution of critical section, reduced serialization, and improved lock and share data locality, as we have discussed. Producer-consumer pipeline parallelism, we've also seen it, but to a lesser extent, perhaps. And we've seen the idea multiple times before. You split a loop iteration into multiple pipeline stages, where one stage consumes data produced by the previous stage. And each stage runs on a different core. And usually in these cases, a stage has a set of data that it operates on. So it's really exploiting locality. In this case, segment N is really stage N. Right? So you can have millions of segments potentially, assuming you can do that parallelization nicely. Okay, the benefit is really stage level parallelism now. And you also get better locality because you're executing, hopefully each stage is operating on some shared data. That doesn't have to be the case, of course. You may not get better locality, but you can still get good parallelism this way. So you get faster execution. So the problem with all of these models is locality of inter-segment data that we have discussed. I'm going to show it a little bit more rigorously. Essentially, if these stages execute on different cores, when stage 1 requires data that's produced by a prior stage, it essentially gets a cache miss. And this cache miss, as we have discussed in earlier lectures, is a communication miss, right? It's really or coherence miss, as we will see coherence later on. So you don't get rid of these cache misses by making caches bigger. There's no way. You cannot manage the cache better. You need to do something else about it. You need to be more proactive about it. The reason it gets the cache misses is because this other stage is producing that data. And when this stage starts executing this load, it will detect that it will get a cache miss, and it will send a coherence request to the cache that houses the latest value of that Y. Makes sense, right? So we're going to see coherence methods later on, so keep that in mind. Okay, so as stage 2 executes its load Z, it will also get a cache miss because this is really a communication miss. The data is produced by a prior stage. In this case, it's nicely produced by stage 1. But it doesn't have to be. It could be produced by some other stage also, right? Maybe stage -1. It's not in the slide. Okay, basically, in accelerated critical sections, as an example, critical section incurs a cache miss when it touches data that's produced in the non-critical section, right? Thread private data. We've seen that. In producer-consumer pipeline parallelism, we never explicitly said that, but a stage incurs a cache miss when it touches data produced by the previous stage. And performance of stage execution is limited by inter-segment cache misses in the end. And we have some analysis of this in the paper. Take this with a grain of salt. These are with small core results. Essentially, if you eliminate all inter-segment cache misses, you can get significant performance. We're going to get very close to that performance. But this problem actually becomes bigger as you scale up the number of cores, as you make things more finer grained. That's why I say don't get stuck on these small numbers over here, 10 to 20%. It becomes much bigger as the number of cores increases, and as you want to parallelize even finer grain. Okay, so let me define some terminology. I'm going to give you a mechanism to do this, but this is just one mechanism. There could be other mechanisms that people develop. And again, I will also ask you to think about, we're going to develop a hardware-software co-design method. But I believe actually this can be done purely in hardware in a nice way as well. Maybe purely in software, that's very tough, I think. But purely in hardware is easier. And maybe there are other mechanisms. So let's define some terminology. So I'm going to define inter-segment data as cache block. We're going to still operate on cache block granularity, since things operate on cache block granularity today. But maybe if you go into processing in memory, we should not be thinking of cache blocks, right? It's good to, let's say, destruct some of these concepts as we go into different environments. But we are still processor-centric in this. It's inter-segment data is a cache block that's written by one segment and produced by the next segment. So clearly, cache blocks that house address Y and address Z are inter-segment data. And ideally, we would like to identify them and do something about them such that the processors that need them don't get a cache miss. Right? That's the idea. Okay, we also define a generator instruction as the last instruction to write to an inter-segment cache block in a segment. So clearly, Y is part of an inter-segment cache block, and its generator instruction in this segment is the store instruction, right? And Z is also an inter-segment cache block, and its generator instruction is the store instruction. Now, there could be multiple generator instructions, which makes things more interesting and complicated because of control flow in programs, right? You may have if and else structures, and if part of the program can produce one data with one store instruction, and else can produce another data with another store instruction. Clearly, when you're executing the program, only one of them will be executed. So because based on the branch you've taken, right? But there could be multiple generator instructions. Make sense? And that's going to be part of the inaccuracy of the mechanism that we're going to discuss soon. Okay, yes. Yeah.
And that S2 requires that A.
Mm-hmm.
A is not the last instruction that S1 expects.
So that's fine. Basically, the definition of the generator instruction is it's the last instruction to write to a particular cache block, not the last instruction to execute. So in this case, it happens that these are also the last instructions, but it could be somewhere in the middle. Yeah, that's right, exactly. We're going to identify these generator instructions, and you can identify these through data flow analysis in a compiler. Okay. Yes, maybe this figure should be nicer so that the generator instruction is also not the last instructions, but yeah. Okay, so basically this work makes a key observation that the set of generator instructions is stable over execution time and across input sets. Basically, the generator instructions that generate these values are producer instructions. You can also think of them that way. And then they're consuming the instructions on other segments. And if you can somehow identify these generator instructions, what you can do, and we're going to identify this in software actually, but you could do this in hardware also, I think. In hardware, you can record the cache blocks produced by the generator instructions, and you can proactively send such cache blocks to the next segment's core before initiating the next segment. And that's the idea over here. And this is the idea that's discussed in this paper. Again, I would like to blur the hardware-software boundary here. Earlier, I said maybe you cannot do this in software. Maybe today's architectures, yes, it's difficult to do it in software. But you could potentially think about recording cache blocks produced by generated instructions in software, assuming you have a hardware buffer that's visible to the software. And you can have a push instruction that basically pushes from that buffer to some other core that's executing the next segment that needs that. So you could actually imagine a programming model assisted by hardware that could enable this purely in software, assuming that hardware is already in place. Right? In current hardware, you don't have that, unfortunately. You could also think about this as it's a fundamental principle is really passing the data to another place, right? It's kind of like you're passing the message in a sense, right? Well, maybe that's not a good analogy. You're really passing the data. You're really pushing the data to some other place as opposed to pulling the data. So existing models of execution usually is based on pulling the data, right? The program basically says load, store, load, store. Store is actually kind of pushing the data, but not to another processor, usually to memory. Now, actually, if you have mechanisms for communication that push the data from one processor to another processor, then you can actually enable a lot of this in software as well, which is very interesting. Okay, I kind of got ahead of myself, but let's take a look at the mechanism. I think I gave you the basic idea, so it's going to be very easy from this point. So compiler, profiler, and hopefully not the programmer, but again, the programmer can, if they want to, identify these generator instructions and insert marshal instructions. We're going to talk about what that is. Marshal instruction is basically pushing the data to the other core that is going to need the data. And you generate a binary containing generator prefixes and marshal instructions. And hardware, when it sees these instructions and prefixes, it records generator produced addresses. And when it sees a marshal instruction, it marshals the recorded blocks to the next core. Okay? So there needs to be some destinations, etc. There are some interesting issues over here that I may gloss over, but you can ask questions. Okay, let's take a look at how the compiler can do this. This can be done exactly, actually. It doesn't need to be profiling, but we did profiling in this particular case. You can exactly figure out which instructions are actually generator instructions in the binary by doing static analysis, assuming you can disambiguate addresses. That may not be always the case, depending on the programming language and memory access semantics that you have. Okay, so in this case, for example, if you profile the program, you will find out that this load Y touches some data that's produced by a prior store. And clearly, this is intersegment data. You can identify intersegment data easily. And you can mark this last store as a generator instruction, not this store, right, in this particular case. You can mark both of them, but then you may be sending some useless data unnecessarily. Okay. So assuming you've identified these generator instructions, then you can insert marshal instructions. And marshal instruction needs to specify when to send. The existence of the marshal instruction basically says this is the time to send the data. So you can actually put it in an appropriate place. And also it specifies where to send the data, in this case, core 1. This needs to be some virtualized ID of the core. It cannot be physical, otherwise programmers really using physical assignment onto the cores. So there are issues like this which needs to be taken into account. But you produce a marshal instruction, okay? This doesn't have to be the last instruction also. Again, it could be somewhere in the middle. In fact, it's better if you can schedule it much earlier, right? Because if it's the last instruction, the segment is ending, and the other segment is probably going to start very soon, and you're not going to overlap a lot of latency, probably. Okay, so that's the idea. So clearly, this spans across the stack. In this particular implementation, the profiler or the compiler needs to identify generators and insert marshal instructions. The ISA needs to change also. You need to have a generator prefix. I need to add some push instructions. I like calling them push instructions also, but marshal instructions. And as I said, library and hardware needs to change such that you can bind the next segment ID to a physical core. So that the programmer doesn't need to know which core a particular segment is executing in. So there's some hardware analysis that I will not go into a lot of detail, but we're going to use this marshal buffer, which stores physical address of cache blocks to be marshaled. You're going to see an example of this. And we see that you don't need a whole lot of entries for this, but in some cases you do. So there are some communication patterns and programs where you may need more than 16 entries, and that's where we're not going to get a lot of performance. But if you increase the size, you're going to get a lot more performance. Clearly, you need to execute the new things. You also need to have the ability to push data into another cache. This is the part that is not exposed to programmers as much today in many ISAs. Okay, so there are advantages and disadvantages. One is hopefully you get timely data transfer. So you can think of this as a prefetching mechanism also, right? Except prefetching is not done by the core that needs the data. Prefetching is really done by the core that produces the data, right? Producer-induced prefetch, in a sense, right? You can think of it that way. I still like calling it producer-induced push of data somewhere else. So basically, you're pushing the data to a core before the core needs it. Another advantage, you can marshal any arbitrary sequence of lines. So we actually looked at ways of doing this with pattern identification. So for example, if you know which cache blocks are going to be touched, you can record them, for example, and you can replay them, kind of like a memorizing prefetcher. But in this case, we're really executing the generator instruction and then sending the data. So it's more arbitrary, it's more general. And it actually has low hardware cost. So essentially, there's no need for hardware to find the generator instructions. But as I said, that has a downside also. Now you need to modify the software. So it may be actually better to have a hardware approach completely. That way you don't need to modify a lot of things on software, right? I don't think it's that nice to keep adding hardware for everything. But there are some realistic reasons why you may want to just modify the hardware, because now you don't modify anything else in the system, right? Okay, so there are clearly disadvantages like profiling and ISA support. And you're not always accurate because what we do is profiling-based identification. But even if you don't do a profiling-based identification, it may not be as accurate depending on the path you've taken. So a generator set is really conservative in our case. And if you push some data that's not needed by a next core, you essentially cause pollution in the caches of that core, right? And you also waste bandwidth on interconnect. Clearly, this is not good for performance or energy. But we find out that this is not a huge problem because the number of intersegment blocks that are communicated are actually usually small. Yes? Yeah. Offline, yeah. Profiling is offline, basically. Yes. That's right, yes. The particular approach is offline. You could, of course, have an online profiler as well, but that's not what we examined. I think online software profiling is probably a bit heavy-handed. But online hardware profiling, if you do this profiling in hardware, it's probably easier to do. And it's probably better for performance because you don't have the overhead of software profiling things. Yes, exactly. Something like that, essentially, yes. Yeah. Those are all interesting things. And just-in-time compilers are also employed. But if you keep adding more and more stuff at a fine grain to just-in-time compilers, it may be expensive. That's why we went with static profiling here. Okay. But of course, you always have the downside of profiling whenever you profile, as we have discussed in earlier lectures, right? Input set representativeness. Okay, so let me give you an example of how this works very quickly. These are the binaries that are generated for two segments over here, non-critical and critical. This is an example of ACS. We add a Marshall buffer to small cores. When the non-critical segment that's executing on that small core gets to a generator instruction, it puts the address of that instruction into the Marshall buffer. And there could be multiple of these that are put into the Marshall buffer. When it gets to a CS call instruction, which is critical section call for a particular critical section, it basically, there's hardware, special hardware, when as this instruction executes, there's special hardware that goes through the Marshall buffer, takes each address, accesses the small core's cache, and takes the data and sends address and data to the large core's cache, L2 or L1, depending on the analysis that you've done. Well, depending on which one you want to push the data in, right? Ideally L1 actually, in this case, but we're showing L2s over here. Okay, and hopefully when the critical section starts executing on the large core, it gets a cache hit when it does a load Y, right? It all depends on, of course, the distance, but you start the access earlier. And this critical section may not start executing right away because it may be delayed, especially if it's a contended critical section. There will be other instances of the critical section that's executing on the large core. So the timeliness of this prefetcher actually becomes better because of contention. And ideally, you want to send the contented critical sections to the large core, right? So what you're trying to do by bottleneck acceleration is actually going well nicely with what you're trying to do by pushing the data. Okay, so we evaluated this again using similar workloads to ACS, and we see this improves the performance of ACS significantly. Some workloads better, some workloads it doesn't matter, maybe this is not a big problem. But clearly on workloads where it matters, you can get the performance benefits. And ideal is actually the blue one. So we get very close to ideal. So it's almost perfect mechanism, which is nice. Yes. Mm-hmm. Yes, but you can identify that, right? Maybe when you get a marshal instruction, one part that I omitted was basically when you get a marshal instruction, you need to do this translation from the virtual core ID to the physical core ID. You can easily identify whether you're in the same physical core. Yeah, that's a good point. I think you want to avoid extra pushes to your own cache, right? Okay. Okay. So let's take a look at an example with pipeline parallelism also, because this is actually more beneficial with pipeline parallelism. There tends to be more communication in pipeline parallel workloads, because the workload itself actually is consisting of these pipelines, right? Whereas critical sections may not be the major thing in even critical section intensive workloads. Here we essentially add marshal buffers to the small cores, and again, when segment 0 gets to a generator instruction, it stores the address over here. And when it gets to a marshal instruction, it accesses its own cache, gets the data associated with address Y, and marshals the data to the next core, to the corresponding core's caches. And hopefully, again, when this segment gets to it gets to the instruction that's loading Y, it will get a cache hit, or at least reduce access latency. Okay. We evaluated this again with the same workloads that we did, for pipeline parallel workloads, and you get more benefit over here. And here, because there is more communication, the 16 anti-buffer doesn't work for some workloads as much. So you still get very close to ideal, as you can see, but you can actually improve this by adding a bigger marshal buffer for workloads that need that larger marshal buffers, because there's more communication that happens across segments, which is interesting. So there's more analysis in the paper that I will not get into, but you can see that the coverage is actually pretty high over here. You can cover almost all misses. Accuracy is relatively low because of the profiling, so you could do better over here. And timeliness is usually quite good, as you can see. Whenever you want to access the data that's coming from intersegment data, you get a cache hit, essentially. And medium accuracy could be bad for performance, but we see that that's not the case usually. But it's bad for energy, of course, right? Whenever you're not accurate, you're transferring something that's wasting energy on the interconnect. Okay. Any questions? I think there's more work to be done in this area. Don't be fooled by the close to ideal results. There are many different types of applications that are communicating. I think integrating this in a general purpose way is actually very important. So, okay, yes. No?
The non-timeliness means that cache miss was already issued by the core.
That's right, yes.
And the data is still in flight.
Exactly. Usually it's still, well, actually, it could be it's still in flight or it's not in flight yet. Yeah. So we didn't break it down that much, at least in this particular picture. It means basically whenever you issue the access, the data is not in the cache. It could be mostly done.
There is
Mm-hmm.
improve the energy efficiency.
That's right.
Making sure that you reach content.
That's right, exactly. Yeah. And also there's scope to improve accuracy. And also there are different workloads. So we examined the set of workloads that, but then some other workloads may have much more complex communication patterns, right? And that exists actually. I know that very well. Yeah. Mm-hmm.
Does the network support multiple requests at the same?
Yes, so in this case, I think it's a ring-based network. Yeah, it's a bidirectional ring. So answer is yes, but it's not as much as what you would support with some other network, as we will see in the interconnection networks lecture. Yeah. Okay. Okay. So we actually have interesting scaling results in the paper. The performance improvement of data marshaling actually increased with more cores. higher interconnect latency, and larger private L2 caches. And the interesting thing is, all of these are happening, right? Meaning this is an idea that could actually be much better in the future. And whenever I think analyze some idea, it's good to look at the trends. Clearly, we're adding more cores to systems today. We're having higher interconnect latencies today, and we're having larger private L2 caches. Although with memory-centric computing, we want to get rid of them as much as possible. I think with memory-centric computing, we want to get rid of especially the second two. More cores are still useful, I think, because you want processing near memory. But still, I think these trends are a bit hard to change. And the main reason why is, with all of these trends, inter-segment data misses become a larger bottleneck. If you have more cores, you parallelize your program more, and you get more communication, essentially. If you have higher latency, you get longer stalls due to communication. And as I said earlier, as you get a larger L2 cache, these misses are the type of misses where larger caches are useless, or better cache management is useless, right? Because these are not capacity conflicts or cold misses. Well, you could consider it a cold miss from the perspective of the core that actually executes the segment, execute that load. Yes, that's true, but that's from the global perspective of application execution, it's not a cold miss, right? Somebody else is generating this data that is causing the miss. So basically, it's a communication miss. And I think these misses are going to be more and more important in the future. That's one of the reasons I spent some time to discuss this. It's a harder area to do research in, but I think it's a very important area. So in the paper, we also discuss other applications that I'm not going to talk about. This could be generalized to other stage execution models, like clearly task parallelism models that people use in the field. I'm going to briefly talk about that when we talk about multiprocessors, I think. And special purpose remote functional units. There are also other approaches in literature that are interesting that I'm not going to talk about. And I think if you actually reduce the cost of this sort of communication, including with this approach, this could be an enabler for more aggressive stage execution, meaning more aggressive parallelization, right? And this is kind of what people really wanted to do when they initially started with multiprocessing. You really want to parallelize your program as much as possible. One instruction in one core or functional unit. What's the difference that much? NVIDIA used to call their execution lanes as cores, and I used to joke with them. I don't think they're cores, basically. So GPUs used to have these huge core, many cores, right? But yeah, maybe from a perspective, functional unit can be considered a core also, right? It's good to think about that. But basically, the reason is you lower the cost of data migration or communication. And this is really an important overhead in remote execution of code segments. And you can always think about parallelism as remote execution, right? What does parallelism mean? You're really executing some piece of code somewhere else, and that's remote. And it's good to think about that. And if you actually make remote execution of finer grained tasks more affordable, more feasible by reducing the overhead that's caused by them, you get much finer grained parallelization in multi-cores or whatever you're communicating. I think a lot of these ideas could be applicable, for example, to models where you actually do parallelism in memory as well, right? Because in the end, at some point, you're going to communicate. Local data, hopefully, is not a problem if you've done a good job in partitioning your data in memory. But at some point, you need to communicate across different, let's say, processors or execution units in memory, and your bottleneck will be this. Good to think about that. Okay. So I don't want to go through this in detail. I think we've discussed all of this. But I think basically what's even more interesting in this sort of approach is you can enable new models, very fine-grained remote execution, as I kind of mentioned. Okay, and that's the paper. If you're interested, you can read it. I think it's going to be part of the homework. You can, as an optional one. Any questions? Otherwise, I'm going to switch to other things in heterogeneity a little bit. Okay, so let me switch to other things. Clearly, heterogeneity is something real today, right? People are having heterogeneity in both microarchitecture as well as architecture, ISA, and existing systems in a widespread manner. But I will mention that there are other uses of asymmetry. So we focused a lot on performance, scalability, and also energy efficiency that comes with all of that. But even if you may not get performance, there there are good reasons to use asymmetry, and one is energy efficiency, right? So there are works that discuss this, and clearly these works are important. Basically, the idea is to implement multiple types of cores on a chip, monitor the characteristics of a running thread, for example, by sampling what kind of energy you're spending, what kind of performance you're getting periodically, and dynamically pick the core that provides the best energy performance trade-off that you think will happen in the next phase, in a given phase of a program. So in this core, best score, of course, depends on the optimization method, whether you're optimizing for performance or energy delay, etc. You could optimize for different metrics, clearly. That's the beauty of heterogeneity, as we discussed, right? And this is a nice approach, clearly. So when this was proposed, it was proposed by folks who were actually working on alpha processors also. And they basically demonstrated these different alpha cores. These are called EV4, EV5, EV6, EV8, which was never built. Because I guess they were bought and then somebody didn't want to build those processors. Actually, they were bought by Intel. And then Intel didn't want to continue this line, clearly. But maybe they should have reconsidered in hindsight, who knows? Okay, but basically, if these cores are already built, EV4, EV5, EV6, EV6 is alpha 21264. I think EV4 is alpha 21064. I don't, yeah, that's true, I think. So this is an out of order processor. This is a heavy out of order processor. These are the relative sizes of the cores scaled to 0.1 micron, which is still pretty large today, right? You can see that these are, EV4 is actually very small. EV8 is 80 times bigger. So there's something to be said about area as well. And these are what's reported in the paper in terms of peak power, average power, and performance across some workloads. I think these numbers are a bit more realistic compared to the Intel paper that I mentioned yesterday, although I'm going to mention that paper because that paper has value independently. But you can see that these folks say EV4 has a peak power of this, and performance is normalized to that. EV5 has a much higher peak power, but performance is 30% higher. And EV8 has huge peak power, as you can see, comparatively. I don't know if these numbers are correct, actually, because EV8 was never implemented. So take that with a grain of salt. But performance is also double, let's say. Anyway, basically, you have a variety of cores with variety of performance and energy and power characteristics. Now, one way of utilizing these cores, assuming you've implemented all of them on your chip, since you already designed them in the past, why not put all of them in your chip, right? That's one way of easing the design of heterogeneous cores. Now, what you can do is you can monitor what kind of performance you get on different cores for different phases of an application. And this is one application, I don't remember which one, but you can read the paper. It shows what kind of instructions per second performance you're getting. Clearly, there are some phases, right? There are some phases where EV8 is much higher performance than EV6, EV5, EV4. And there are some phases where their performance is similar, right? And this could be because you don't have a lot of instruction level parallelism to exploit in EV8 in some particular phase, whereas in some other phases, there's a lot of instruction level parallelism to exploit, etc. And the idea is basically to determine those phases where you would want to schedule the code on a different core based on some metric that you're optimizing, and then you schedule it on that particular core. So their dynamic mechanism, if you look over here, if you want to optimize for energy, chooses some of these cores. So this is basically, I think, their dynamic mechanism. It decides to choose EV4 only very infrequently. It chooses EV6 most of the time, as you can see, and sometimes chooses EV8. And this is if you want to optimize for energy delay product. Okay, I'll let you think about it. That's the paper. Clearly, there are advantages and disadvantages to this. Now you get more flexibility in energy performance trade-off, and you can execute computation to the core best suited for it in terms of energy, right? Assuming you're taking into account energy directly. Clearly, there are disadvantages, but this is true for disadvantages for a lot of heterogeneity. If you do an incorrect prediction, you get to the wrong core, you get reduced performance or increased energy. This is more of an issue in this case because you're not really picking a critical section of a program, right? You're really picking some program. You may be migrating a program from one place to another, and really wasting performance. So if you do the wrong decision, this is not good, clearly. If you do the wrong decision in critical sections, yes, it's not good, but you're not migrating the whole program. Whole program migration, because if you do that now, you need to warm up your caches in the other core also. Okay, there's overhead of core switching, which is part of whole program migration. So these are actually relatively similar to the disadvantages that we see. I think incorrect predictions are actually very dangerous here. Yeah, you need to design multiple cores, but if you already have them, maybe that's good, or you could argue that that's good at least. It reduces your design effort. You need to have phase monitoring and matching algorithms. I think these are important actually to develop independently of whether or not you do this. Identifying the phases of a program and deciding what kind of hardware to use for a given phase is really an important problem that's still not completely solved. This could be done at a coarse granularity like this. You identify, okay, this is my phase, and in this phase, I use a large core, right? But you could also do this phase-driven configurability at smaller granularities. This is my phase, and I think in this phase, this prefetcher configuration will work nicely. You don't have to migrate things to a large core, right? So there's a lot of benefit to doing good phase prediction. So what characters should be monitored is important. Once characters are known, how do you pick the core in this particular case? Okay, any questions? Yes? That's also true, yeah. I think in this case, they did like, they chopped the execution time into intervals, basically. That's one way of doing it. But of course, if you have more information, if you can identify the changes, like in behavior of code, potentially with software support, you can do better. In fact, that may be even better because you may make less or more informed decisions. Mm-hmm. Exactly, yeah, exactly. So this doesn't consider utility, for example. I think you mentioned some other thing. Maybe more utility-based metric could be better, right? Okay. So there's room to improve, as you can see. Actually, there later works kind of looked at the utility. That's performance impact estimation work that I didn't talk about, but we compared to in the utility-based acceleration, tried to understand the performance impact of moving from one core to another with some metrics. It was not exactly utility, but it was getting closer to utility. Okay, so we've talked about asymmetric and symmetric cores. Let's start wrapping up a little bit. Clearly, if you have asymmetric cores, you can provide better performance when thread parallelism is limited. You can be more energy efficient also at the same time. Disadvantages, of course, more complexity. Basically, I think we've kind of seen this earlier, but you need more complexity. You need to design more than one type of core. If you already have them, that's great. But if you already have them, that may not be a good match also, right? Maybe you don't have the right core for extremely high parallelism, right? As we have seen earlier, like EV4, actually, in this particular case, EV4, let me go back, is a core that's still a little bit expensive. Let's say it's not out of order execution, it's in order execution, but it has branch prediction, etc. So it's expensive still. Maybe you want very, very cheap cores, right? To really design. But maybe the design effort of cheap cores is smaller. We could also argue that. So scheduling should be more complicated. We've already seen this also. What computation should be scheduled on the large core versus small core? Who should decide this? Hardware versus software. Managing locality and load balancing can become difficult if threads move between cores. This is actually interesting. We have not discussed as much, but especially if threads keep hopping between cores, now you have another problem because your working set, data working set, and instruction working set should also be hopping between cores. Meaning whenever you get scheduled on another core, you may not have you may get a lot of cache misses to begin with, right? That's locality. There's load balancing also. Programmer may have tried hard to balance the load, assuming that your code is executing on multiple cores. Now underneath, you're moving things. How does that load balancing change, right? So load balancing is a tough problem, as we will see a little bit more. And cores may have different demands from shared resources also. That's something important to think about. Like how do you actually provide access to different cores to shared resource, like the memory controller, caches, etc. Okay, with that, I think let me talk a little bit more about how to achieve asymmetry. We've discussed this a little bit yesterday. You can have static asymmetry. You can have dynamic asymmetry. With static means that your type and power, of course, are fixed at design time. Dynamic means these change dynamically. Right? With static, people have looked at two main approaches for designing faster cores. Basically, you have hard-coded high frequencies, static higher frequencies for some cores. Or you can build a more complex, powerful core with an entirely different microarchitecture, including frequency potentially, right? With dynamic, and then there's some natural asymmetry, right? As we have discussed yesterday. Even in cores, there's variations in chip byte frequency. So some cores may naturally be faster, some cores may naturally be slower, depending on the variation. And if you can identify that, maybe you have higher frequency and higher voltage for some cores and lower frequency and lower voltage some other cores, if it's static. Dynamic is, of course, more powerful in general. Basically, one way of achieving dynamic asymmetry is by boosting frequency. I'm going to talk about that a little bit. That's an easy way of achieving. That's why everybody did this earlier. Now people are doing asymmetry also. So both of these are done. Well, not the dynamic combining. That part is not done. But boosting the frequency dynamically is done. And static asymmetry is done today. But also there's another way of dynamically achieving asymmetry, which is combining small cores to enable a more complex, powerful core. I think that's a very interesting approach that needs to be re-examined perhaps again. But I'm going to mention some papers that I briefly mentioned yesterday also, but I'm going to put them on a slide. We'll not go into that much today. Okay. Maybe there's a third, fourth, or fifth approach that I don't know. So the second approach, to combine small cores to enable a more powerful, complex core, there's actually works in this area, which I believe are interesting. I'll just leave it here and not talk about it. I believe morph core is actually the state-of-the-art approach. Clearly, it's the latest compared to all of these, and it actually is a more implementable way of doing it. Some of these are actually very interesting ideas, but much harder to implement. Like core fusion, I think, is a very interesting idea, but much harder to implement. Okay. Let me talk about asymmetry via frequency boosting, because this actually opens up interesting issues. As I said, this is already employed in today's systems. Today's systems, for example, when there's a single thread running, the frequency of the core that's running that thread is boosted significantly. It's called turbo boost at Intel. I don't know what's called in AMD, but it's kind of similar. Essentially, you do turbo boost and you increase the frequency of that core. And the reason you can do that is because you now put all the power to that core, and the other cores are not running. Essentially, they're not consuming power. Right? So this was, okay, before I go into that, there are ways of doing this statically. Due to process variations, cores might have different frequency and statically tied. And simply, you can hardware or design the cores to have different frequencies. And then you can migrate an application from a low frequency core to a high frequency core whenever you want it to have high frequency. Right? You would, of course, have some cost of migration, but it's possible to do. Dynamic is already done by doing dynamic voltage and frequency scaling. That's nicely described in this paper by Intel. You can actually achieve this. So let me go over this a little bit. Basically, the idea in this paper was also interesting. Basically, their goal was to minimize the execution time of parallel programs while keeping power within a fixed budget. And their observation is similar to what we have discussed earlier. You want the best scalar performance when you actually have a single thread. You want the best throughput performance when you have many threads. And there could be some intermediate points also. And the idea is to, you normally have a fixed power budget. And what you can do is you can have a lever to play. And this lever to play could be energy per instruction that's consumed. So by changing the energy consumed per instruction, while the power is constant, you can change how many instructions are executed per second. Right? Does that make sense? And that's the idea over here. Now, this may not be intuitively mappable to asymmetry, but it's actually easily mappable to asymmetry also. If you're in a high throughput phase, reduce the energy per instruction and execute things in many small cores that require low energy. And this naturally enables high IPS, instructions per second, right? If you're in a, let's say, low throughput phase, increase the energy you spend for each instruction but you're going to execute probably a smaller number of instructions, meaning executing a large core, for example, or multiple large cores, etc. That's the idea over here. So I've already said this, I think. For a fixed power budget, run sequential phases on a high EPI processor, high energy per instruction processor, and run parallel phases on multiple low energy per instruction processors. And now we have asymmetric multi-core again. Okay, so that's one way of achieving it, right? So clearly you can do this energy per instruction throttling using DVFS as well, not asymmetric multi-core. Actually, in this work, they didn't really talk about asymmetric multi-core as much. They achieved it through DVFS. But I like this approach because this applies generally, as we will see later on also. The key is really, if you think about it, asymmetric multi-core is really modulating the energy per instruction to match the IPS that you really want, right? But there could be other ways of modulating the energy per instruction, and that is through DVFS, for example, dynamic voltage and frequency scaling. In phase of low thread parallelism, you can run a few cores at high supply voltage and frequency. And in the extreme case, one thread exists, you run one core at the highest supply voltage and highest possible frequency within the power budget and thermal budget. In phase of high thread parallelism, you run many cores at low supply voltage and low frequency. Okay, so there are other ways of modulating things, which is also interesting. This is not a comprehensive list, but this paper, this other paper that's actually earlier from also Intel, discusses other ways of modulating the EPI. One is voltage and frequency scaling. Clearly, when you do voltage and frequency scaling, you may increase or lower voltage and frequency. In this case, they basically say, lower voltage and frequency so that they get a lower EPI. This is according to them, the EPI range, the range that you would get energy per instruction from 1 to 4. Take all of this with a grain of salt. And then there is also a time to change the energy per instruction, right? Meaning time to achieve that state where you're running faster or less fast. And according to them, at the time, it was 100 microseconds. You need to ramp up the voltage, essentially, right? This changed over time, but there's always time to actually throttle the EPI. Okay, so this is voltage and frequency scaling. You could do asymmetric cores, and according to them, again, EPI range is higher. So you can actually get higher performance as well as energy range. According to them, migrating a 256 kilobyte L2 cache takes 10 microseconds or so. So there's some more effort over here. Again, take all of these with a grain of salt, but there's more time according to them. And we already discussed the action. And then you could have a variable size core, meaning you can have a single core, but when you don't have enough instruction level parallelism, for example, what you can do is you can reduce the size of the structures of the core. They're not talking about caches over here, but they're talking about maybe changing the sizes of different structures internally. You can, for example, change the width of issue. You can change the size of your instruction window so that you can make things in order, maybe. I'm not sure if they're talking about that over here because I don't remember, but I don't think this is in order. It's really still within out of order. Okay, so basically there's some cost to it, etc. And then there's speculation control, which is reducing the amount of speculation. That also changes your EPI in some way. Basically, you say, I don't need a lot of performance over here, so I'm going to reduce the speculation that I do on the processor. When I get to a branch, I stop fetching. That's one way of reducing the speculation, etc. And this is clearly the fastest, right? One of the fastest ways of doing it. Okay, so there are different ways, and if people are interested, I'd recommend looking at that paper. And some of these techniques are actually implemented in modern processors. Actually, I think all of these are implemented in today's processors, but the numbers take them with a grain of salt. Okay, so we're specifically talking about frequency boosting. Frequency boosting is clearly implemented. This was the first thing, one of the first things that was implemented. This is very simple to implement. No need to design a new core clearly. And the other big benefit of boosting frequency is parallel throughput doesn't degrade when TLP is high. When you have a lot of thread level parallelism, you still run a core with low frequency, and you still have a high thread level parallelism. You don't need to dedicate cores. You don't need to dedicate the space of many small cores for a large core, for example, right? And it preserves the locality of the boosted thread, which is nice, right? So this, yeah. Of course, this has disadvantages. And one of the biggest disadvantages is improving frequency helps with instruction level parallelism if you're memory bound, if you're compute bound especially, but it usually doesn't help with memory bound workloads. So if the phase of your program is memory bound, you're still memory bound. You may generate more requests more quickly to the memory system and get better parallelization, but the effect of that in the grand scheme of things is actually much smaller. You're better off doing something else with memory, basically. And also, another thing is it doesn't reduce cycles per instruction. This is another way of saying that you didn't design a different core, right? Basically, frequency is only part of, both of these point to the fact that frequency is only part of the performance equation, right? If you remember the performance equation, you can improve the performance of a single thread by changing the number of instructions times the cycles spent on each instruction times the time spent on each clock cycle, right? That's the performance equation that we have. Clearly, we're not changing the number of instructions here because the binary is the same. We're changing the frequency. Hopefully, things will improve. But cycles per instruction fundamentally doesn't change. Actually, it increases because now your frequency is probably larger. Maybe you need to do something else in your pipeline, right? It may increase, so basically. It's good to think about that. But fundamentally, you're not improving cycles per instruction. But whereas if you design a different core, hopefully that has maybe the same frequency, I don't know, maybe better frequency, but maybe also better cycles per instruction. Okay, this is also interesting to think about. Changing frequency and voltage can potentially take longer than switching to a large core. The debate is still out over here. It's good to think about that. There's a trade-off over here, right? Clearly, there's time you spend for changing frequency voltage, ramping up voltage, especially ramping up voltage takes time, right? And if your frequency range is very large, you need to ramp up voltage from a very small value to a very large value. And that is actually, that is a lot of issues. Clearly, it takes time. It takes time to do it reliably because now you're actually inducing a lot of noise in the system. And that noise may actually lead to some power issues. Okay. Where switching to a large core doesn't require changing the frequency. Okay, there are interesting issues. As you can see, even with this trade-off that we go into, there are a lot of issues. Okay, any questions? Oh, wow. I spent more time than expected. So I think I'm not going to cover the remaining slides over here, but I'll go through them. We've already covered a bunch of these. This is more of some vision slides that talk about asymmetry everywhere. I'll let you study it, but essentially, I think maybe I'll cover some of these things very quickly, not all of them. I think one of the biggest interesting things in asymmetry, these are slides actually from 2010. I think I put these slides, I presented these slides in a workshop on, essentially the question in the workshop was, what is the future of computing? Something very general. And one of my visions was really asymmetry everywhere. Essentially, each component should be designed asymmetric. That's the goal, to fit different computation, access, and communication patterns for different power, performance, reliability characteristics. There's nothing you have not heard of so far. But asymmetry, I think, also subsumes configurability and partitionability. And then you need to you design the runtime system to automatically choose the best fit components for each phase. So for a given phase, let's say you determine, you dynamically stitch together a best fit chip for that phase while satisfying the performance SLA with minimal energy. That could be one goal, right? So I like thinking of it this way. I'll go through these again relatively quickly. For example, phase one may want high power, high performance core, some lean cache hierarchy optimized for some access pattern, maybe some lean interconnect, and maybe some type of memory, right? And if you have some heterogeneous things, you can actually dynamically identify this phase and match computation to it. Phase two may require a very small core, but a bigger memory hierarchy, right? Phase three may require a lot of cores, but very lean memory hierarchy, maybe a streaming phase with large capacity requirements, etc. Now, if you could actually design the hardware to be able to do that, it would be nice. And then you maybe when you go back to phase one, you still incarnate this hardware. And then you can also morph the software components to match asymmetric hardware components. You may have multiple versions of software for different resource characteristics. I think this is also very interesting. Essentially, I think you want flexibility in hardware and flexibility in software also to match the flexibility in hardware. So version one may run here. Version two may run here with many small cores. And version three may be heterogeneous also, right? So there are many interesting research and design questions over here. Again, I will not go through these in detail. Some of these we covered in a very limited manner in what we have discussed. But I'll give you some simple examples, like serial and parallel cores. We've kind of discussed this, right? But you could also have a single core that has out-of-order capability and a VLIW capability. And you can dynamically figure out which one to use. VLIW is a very long instruction word, so a compiler schedules the parallelism. Or it could be out of order and in order. And you could switch between them, right? Depending on the phase. And there are works in this area. You can design the memory hierarchy differently for streaming versus random access. We've kind of seen examples of this with prefetchers, etc. But I think there needs to be more over here. If you remember for example, stream buffers, they were getting rid of the caches, right? Earlier. It's good to re-examine some of these things. Today we have these huge caches, and people don't re-examine some of these fundamental decisions, in my opinion. Huge caches are easy to build and easy to put. If you have area, let's waste area, let's put it over there. Let's forget about all of the costs of it. Whereas if you're streaming, those caches are useless, and they actually hurt performance. And we don't have a way of actually streaming easily into the processor today. Okay. So we're going to talk about interconnects. You can have latency optimized versus bandwidth optimized interconnects. We've talked about memory controllers, and you can partition the memory bandwidth or interconnect bandwidth across latency sensitive and bandwidth sensitive workloads differently. Thread cluster memory scheduling kind of does that. You can have different, we've kind of also talked about this, memory scheduling policies that are catered differently for compute intensive versus memory intensive workloads. And we've talked about hybrid memories, right, for different purposes. Okay, well, we've also talked about reliable DRAM versus less reliable DRAM. And we've also talked about heterogeneous latency DRAM and heterogeneous refresh rate DRAM. So we have a lot more today. I'll end here, but this is kind of a vision that I have. I don't think it's easy to achieve this vision in the short term. It's a much longer term research vision. But I believe it can actually yield a lot of benefits going into the future. I think the works that we've discussed today are kind of scratching the surface, right? And the good news is these are already in real products. So asymmetry in both frequency scaling, core sizing, speculation control, and also asymmetric cores finally are in products. Who knows, maybe in future we'll have a lot more, let's say, fluid hardware and fluid software. Okay. Any questions? Otherwise, this is really the right time to take a break. Let's take a break until 14:45, 17 minutes, and then we'll come back with lecture